Good morning, everyone. Thanks for being the brave ones to be here at 9 a.m. Doesn't happen very frequently, or you're so jet lagged the other way around that you haven't gone to sleep yet, like me. Okay, so what we are going to do is I'll start with an introduction.
Can we increase the volume sensitivity on the mic? Somebody said the
Volume of volume of what? The microphone?
Yeah,
Or maybe like
just change that.
Something like that. Is it better?
let me try to see if we're using this one actually. Yes, Epson. I
This is
guess.
speaker.
And I don't know, it doesn't work. That's weird.
I'm asking if the volume's louder now with it.
Okay, so I will so people on Zoom, if there was a problem, am I audible now, or do I still should position myself better?
So
Someone on Zoom?
it's okay, no worries.
Okay, no worries. Okay, in the meantime, maybe we can figure out how this thing works too. Okay, so what we're gonna do is I'll first give a little bit of a more technical introduction, and then we'll go to a schedule so you have an idea of what other talks are coming up, and then we'll take it from there. And so welcome to the tutorial. So I'm going to start with this little motivational video. So here is a fish. You might have seen this video before, but it's always fun. There's a fish that appears to be swimming. And what's special about it is that the fish is actually dead. So there's a string that is connected from the tip of the fish to the front, and the water is just streaming. And what you're seeing is actually the interaction between the body of a dead fish and the water around it, which appears to be actually gracefully swimming. So it's dead, but it's still clearly doing something, right? So it brings up the question that actually, is the fish intelligent? Yes, no. And I mean, it's dead, right? I mean, the brain is not working. How could it be smart? But again, it's like clearly doing something, right? So in that sense, it's exhibiting some intelligence, but the question is that where is the intelligence? Like, where is it housed? So again, like I said, the brain is dead. So if I get the fish and cut into two pieces, and one piece would be the brain and the other would be the body. Now, generally, when we in AI and machine learning, when we are thinking of like developing intelligence, we are primarily working on what looks like the brain, right? The cognitive function, the neural network that does control, perception, and so on and so forth. But in this case, the brain is dead. So if everything is happening, it's coming from the other side. So, so exhibiting intelligence can come from the non-brain part of an agent too. So you can think of it as this agent has some specification. This is specifications by some parameters. Some of these parameters are in the brain, like a lot of it. But also some of the other parameters that makes this agent special is on the right. So there is basically a bunch of parameters that define this complete intelligent agent. And both of them are parameters, but they are characteristically a bit different. The one that is on the left is flexible and fast in learning, like our brain. It sort of keeps receiving feedback every second from the environment and updates and so on. The figure on the right are more rigid and more slow, like the body doesn't adapt too much. After birth, there's some things happen, but it doesn't move that fast. So it's the rigid part is the slow part, but still there are some parameters, still to some extent does adaptation happen. So both parts, like I said, contribute to exhibiting intelligence in the end of the day. So this event generally talks about this part of the graph, the right part, like that's what we call basically the morphology of the agents. Okay, so now morphology is not similar to the example that I provided before, which is more like the mechanical, the physical morphology of the agent, but also perceptual morphology. We can see it in the sensory system, for example, anatomically, the shape of the eye, the positioning of the eye, a bunch of parameters that I'll go through later. So this is also part of the morphology. If you embed it in the previous chart that I showed, there's a slow changing parameters and there's fast changing parameters. And this is very basically diverse. If you look at it, is that there's a lot of, I mean, in the physical body, of course, there's a large diversity, but also perceptually, as we'll go forward, you'll see it is that these diversities, like, why are they coming from? They're a result of basically specialization. So they're different. You can imagine these animals live in kind of different conditions, different ecological conditions, underwater, above water, flying, and so on and so forth. And they have different needs. So the ecology is basically tailored to each of it. And that's where the diversity comes from. And this is basically people like Gibson, what they said, they argued for the role of ecology in vision, for example, that the properties of a perceptual system is a reflection of the environment that is around us. So the environment is specific, it has certain properties and patterns and biases, and that kind of gets reflected in our perceptual system too. And we are saying it more broadly also, that gets reflected in the morphology of the agent, all these parameters and in general. And why is it so diverse? Like I said, is that you can think of it as, you know, there's like little islands of ecology, you know, underwater, above water, like a cockroach that lives in the pipes versus a bird that flies in the sky. There are these little islands of ecologies that they're niches. You don't have to traverse them, and therefore that provides an opportunity to specialize towards each of these, and that's why we have the diversity. Now, at least nature suggests that we don't really have to have one agent that works for everything. And indeed, we might not even want to be able to go there if we can. We can use anecdotally, like a no-free lunch theorem from learning theories, that if you try to be so general that you win everywhere, that means that nowhere you're going to win big, nowhere you're going to be very efficient. So if you want to have like one agent that satisfies all different parts of like tasks and environments and so on and so forth, we are not going to eventually be able to have the agent in an efficient way. So we'll basically see that how designing morphology, how specialization in various forms actually brings efficiency in the end of the day. Just like the fish was very efficient in the sense that the brain doesn't have to stop working, but it still is doing its job, right? But obviously, if you bring it, you know, turn it into a terrestrial animal, drag it on the ground, it's not going to work the same way. So it's being in the right niche environment that leads to that efficiency. So that leads to us wanting to design agents that fit and get tailored to the environment and tasks and needs and so on around them. How do we do it? Is through the so-called like automated design method. So there's this example, classic example from Carl Sims, Evolving Virtual Creatures from 94, so 30 years ago now, that it basically was an automated system that through an evolutionary algorithm, it basically assembles a number of like primitive parts in order to satisfy downstream utility. In this case, it was primarily more mobility oriented. So you can see that, you know, it obviously satisfies the property of the objective of mobility. Of course, sometimes it leads to weird answers because it's only satisfying mobility. It doesn't, for example, minimize energy consumption or contact and muscle and tissue damage and so on and so forth. But it is an example of computational design in the sense that these shapes that are solving the problem are entirely emergent as a result of an algorithm interacting with the environment. Nobody has engineered them more than engineering what you see on the left in terms of primitive parts and so on. So that was 30 years ago. Things have gone forward in the meantime. Now we have things that are a lot more effective, mostly due to advances in computing, a lot more compute, so a lot more parameters to optimize, new optimization, a lot of new mathematical models and simulators that we have that we will see later that how it is used actually in the design. And also machine learning has come to rescue where we don't actually have these models. So I think it's useful to have a little bit of a structure of how the automatic design methods work. And I would actually approach it this way, is that let's say there are two sets of parameters, two spaces. One set is the design parameter space, and another one is the downstream goal. The design parameter, you can think of it as, let's say we want to design the mechanical body of a robot. So we parameterize it with where the voxels are and some physical properties of them, for example, elasticity and so on. And the other space is the utility that we are looking for example, running faster. So we want to design this left part in a way that the agent on the right, after the controller is applied to it, it actually runs faster. So the way it works is that we typically have a model that relates this space, the left space to the right space. And we use this model as a result of this linkage is that we can now use classic optimization ideas in order to set a goal here, maximize it, and get the arc max of the left. So Now, useful categorization is one way of it to look at it is that where these models come from. So one category of methods that we'll see today is they have physics-based, for example, knowledge. They have physics-based knowledge about a certain domain, for example, Newtonian mechanics, that turns into a compact mathematical form. So we will use this as the model to relate this thing to that thing, and we'll use more standard optimization techniques for it. So that's a physics-based, for example, view. But sometimes we don't have these models. We don't really know how to link these two to each other. And that's as usual, whenever we don't have a model, we approach it with data-driven learning and we learn a model. So for example, vision mostly is in the learning base. The perceptual morphology is in the learning base, because let's say we have some property of the eye or parameter of the vision system, and on the right we want to have perceptual behavior that are competent and so on. This thing goes through basically cognition. Eyes see something, goes through the brain, and then behavior comes out. We don't really have a compact mathematical model of it. So this thing, doing perceptual design, usually ends up learning an approximate model through data-driven learning, and then use it as a way to do the optimization. So we'll see it in Andre's talk, for example, that everything that happens perceptually is through this process. And also it's useful to remember that this general methodology is similar to other fields, not just computational design in the context of robotics and vision, for example, X discovery, like material discovery, drug discovery, and so on and so forth. So they basically do the same thing. They find a model that relate the input space to output space. This is the output spaces where they care about. For example, the input could be, various chemical compositions, compounds of different compositions, different compounds. And on the right is that what kind of impact that can have on the body of a patient who takes it. And so they learn a model, for example, is that they have a data set of known compounds and known effects, and they learn a model and then use that model to sort of go back and search in the original space in order to find, this time propose some new compound in order to maximize some certain effect, like maximally reduce fever and so on and so forth. And they go through clinical trials and so on to see whether that's actually correct or not. But that's generally one of the main ways that the X discovery pipeline works. And gameplay too, like AlphaGo, you learn a model of actions in the space of the game, so actions towards utility, and then you use that basically to search and plan and so on. But it involves learning a model and doing some searching and planning on top of it. So in this piece of the related problems, one of the talks will be from neural concept, which is interesting because it solves, for example, aerodynamic problem on designing airplanes and cars and so on. But it's an industry solution. They're actually selling it to various companies. Last time I heard they actually had a contract with Airbus. If I remember correctly, we can ask Pierre. So it's interesting to see one that actually works and is being sold, and is going to be the last talk of the day right before lunch. So in terms of related fields. And one last thing that I want to say here is that, is it actually worth, or when is it worth to do the computational design rather than manual design? So it is worth under the following conditions. Like when we are not good at understanding like what matters, basically then we anthropomorphize too much. So an example here is the zebra and a lion. So zebras have these distinctive patterns, right? Why do they have them? Any guess? Yeah.
Yeah. So say that they try to avoid flies from taking them, and another one gets, if they stand in the crowd, it's harder to fall for.
So yeah, you're very sophisticated for exactly. So you have both answers that I wanted to cover in it. So usually people go say, oh, it's a camouflage mechanism, right? So the lion, when they blend in the background like zebras and so on, because of course, like deer and so on, it's a very common, the patterns are for camouflage, or when they stick together as a herd, they look bigger than what they are. So there's just, it's not actually the case, because we are basically anthropomorphizing too much. We're looking at it too much like a human. The predators, lions and so on, they don't have that high resolution of a vision compared to humans. So from a distance, especially when they look at it, they don't resolve the patterns, actually. So a donkey and a zebra are indistinguishable from each other to a lion. So that is not the reason. The reason is exactly like the mosquitoes. So mosquitoes are as big of a problem, like a death threat to zebras and so on, compared to lions, so blood-sucking mosquitoes. And actually, there are farmers that paint their cows and so on with zebra patterns as a like mosquito repellent mechanism, and it works. So, well, yeah, we figured it out, but if we wanted to design it with that world model that we had, is that, oh, this should be camouflage and so on, it would be going wrong. And generally, domains that get increasingly unintuitive, they become increasingly harder to design them intuitively. And I mean, this is not just a scientific thing, also from an engineering perspective, there are plenty of perceptual systems that we have. They don't look like a robot that live in our household, but instead they're basically, something called pill cam is a pill that you take, but it's actually a camera. And as it goes down, it records a video, and it's used for diagnosis and so on. And ultimately, they want to make them active instead of being just passive that is being swollen. So if they get stuck, they can do a little bit of vibration to unstuck themselves. Or eventually, they want to make them much smaller to be able to inject it in the bloodstream. So now imagine these perceptual domains, like how does it look? Like it's very unintuitive to us to be able to even design them in the first place. So computational design actually has the potential to be at least less biased in these cases. Okay, so now in schedule, so there are two parts. The morning is primarily about vision, and afternoon is primarily about robotics, the mechanical, the physical morphology. So first, I'll finish off with a few more like case studies of different parameters that contribute to the perceptual morphology. Then Andre will talk about an actual computer vision case, not just motivations, but a project in which several of the parameters, the morphology of an agent is designed computationally, and it does work, and it has somewhat like interesting and surprising answers, such as you can use very low resolution cameras, very efficient ones, solve problems that would be hard to initially think they can be solved the same way. And so there's generally little work in the space of designing perceptual morphology. There's a lot more in the space of robotics. So Andy is the expert of the robotics, so he'll give you a crash course on that. But in the morning, we are gonna go through a few different phases, but just that's the state of the field, that there hasn't as much work on perceptual morphologies. So then we'll have Sonki. Sonki is, we are very happy to have him because he's a real biologist, not me that I'm just, shadowing being a biologist here while being a computer vision, going through biological cases. So the diverse cases studies in the biology are always basically motivations for what we are discussing today. There's always diversity, there's always adaptation to the neighboring environment. And therefore, it makes sense for us to ultimately design our robotic agents and perceptual agents that way, like bring the body into it and design the body rather than the sort of disembodied LLM thing that only lives on the internet, that plays a role too, but ultimately when it comes to cyber physical system, this body matters. And biology is examples of that. There are plenty of it. So he will give us a set of cases from an environment that is somewhat alien to us, like deep dark in the ocean, deep down. And you'll see that actually how this space really accommodates new forms of morphologies. And like I said, Andy will talk about the mechanical part. And then comes the neural concept one, the industrial one. So is there any question up until this part of the introduction? This would be a good point before I move forward. Any? And please ping me if there's something on Zoom too, in case of that. Okay, so it's useful to look at kind of more cases of specialization when it comes to vision only. I'm going to abandon the mechanical morphology for now. Is that how much diversity actually exists really? Because again, if you look at, we look at it as humans, it might look like the cat's eyes and dog eyes and human eyes and so on. They kind of look kind of the same. And this is not just about the eye, the entire, perceptual system, but we use eyes because these are anatomical examples that we can directly inspect. So is there really a lot of diversity? The answer is yes, at least compared to our computer vision system. So in computer vision pipelines, we typically go with like an ordinary camera, like a lens-based camera with CCD or CMOS, many megapixels, and so on and so forth. And at least compared to this pipeline that we have, nature is a lot more diverse and specialized. And think of that no free lunch theorem kind of a story that I said in the beginning, is that it's really, this is not bringing us that efficiency, is not benefiting from those things that we discussed. So let's go through a few cases, a few of these parameters of design that are common, at least known so far. And it's more than that because really when we do end-to-end learning, we can design all of the parameters, many parameters that might not be exposed and obvious and discrete in this sense, but at least these things exist. Like a field of view, the first one, like the most common, intuitive one is that placement of the eye. For example, predator animals versus prey. Predators usually have the preys, they usually have eyes on the side because that gives them a wider field of view because they can detect the predator coming from any direction. And that's very useful for survival. On the other hand, predators, they're more likely to have eyes that are frontal. So they have overlapping field of view, and that gives them a sense of depth, and that's better for targeting and so on. And they give up that high field of view. They have plenty of blind spot, but because they're not at risk of being preyed, then they don't care about it. And so this pattern is relatively common. You can look at birds, for example, hawks versus dogs, and so on. So one pattern. Another pattern that is similar is pupil shape. So you have seen cats. The cats have these vertical pupils, but it's an ambush predator. And then there's the goats and sheeps and those things that have these horizontal pupils. And the reason is very similar. So these horizontal pupils, this sort of opening, it gives slightly higher field of view, which makes sense because compared to the predators, these things have to watch for things coming from different directions more. So this pattern is common. All of these patterns have violations too, because none of them is the singular rule that applies, but they're one of the many rules. So generally, you can pretty clearly see two modes that conform to them. Sometimes the adaptation is degradation, and in this case, I would actually call it like simplification, like as a good thing. So, for example, there's this fish, and what's distinct about it is that it doesn't have eyes. So what happened is that there's a type of fish that was on the surface but migrated to the cave. And what's in the cave? There's not much light. It's kind of too dark. So vision is not really that useful. So it kind of evolved to get rid of this uneconomical toy that it has. Vision generally uses a lot of metabolic energy. So if you don't use it, you better get rid of it. So it's not like they didn't have eyes in the beginning. They had eyes. They migrated to the cave, and they lost the eyes evolutionary. Oh yeah, this is their surface cousin that is very similar, except that this one migrated, this one didn't, and then they branched off in terms of eye. And our example common thing is darkness adaptation. Animals live in the dark. There are plenty of nocturnal ones, and there are form of adaptations and specializations that happen that comes with its own tax, but it's useful. So tarsiers, like one obvious trick is that if you want to adapt to the dark, what do? Like just make your eyes bigger. So they have a bigger aperture, bigger opening to collect more light, so you see better in the dark. So that's a common trick, like tarsiers are like that. They have these huge eyes. Their eyes are actually as big as their brain. This is their eye, and this is their brain. And compared to humans, this is the brain proportionally, and this is our eye. So you can see that how drastic this adaptation in terms of size is. But there are other forms of adaptation too. For example, reflective coating. So you have seen deer and cats and so on. So they have these, when you shine light into their eyes, like with a torch, or when you're driving, their eyes are reflected, right? That is a darkness adaptation mechanism because when light lands on your retina doesn't absorb all of it. It misses some of it. The efficiency is not 100%. So some of it passes through, but when it's so dark, you need to recycle it. You cannot afford losing it. So there's this reflective coating that acts like a mirror, then reflects some of it back. So it can recycle some of the photons that have gone through. And so that's another darkness adaptation, or sweat bees basically integrate the photoreceptors to go integrate an area when there's not enough light to distribute among them, to basically they swap resolution for sensitivity to light. So they integrate 5 of them. They use it as one photoreceptor as if they were bigger in the first place. Another case is number of phobias. So phobia is the high resolution area in the vision. Humans have one. It's roughly like as wide as your thumb when it's extended to arm length. So that's where you see a high resolution. Everything else around it is blurry, and we have one of it. So phobia is basically a pit on your retina, which has the high density of photoreceptors. And then there are other animals that have multiple of these. For example, hawks and falcons, they have 2 of them. So they see 2 points in high resolution simultaneously, supposedly because, again, they do something that they benefit from it. That leads to sort of spiral patterns of flying and a whole bunch of behavior too. Another thing that is obvious is the placement of the eye. So we saw, how the placement can lead to a higher field of view. But then there's, in terms of predator prey, but even for animals that are not, even are not terrestrial, still the same thing. Placement of the eye seems to be an important parameter to optimize. So the clams, these are clams, the sea clams, that they have a lot of eyes, somewhere between 200 to 300 eyes. These little blue ones are eyes. So they're distributed around the shells, upper and lower. So they have a particular placement. And so basically decided that instead of packing them and create a dense grid and create a high resolution image, just like, for example, the way our eyes work, they decided that it needs to go with a distributed solution. And resolution also is one of the interesting ones because humans have one of the highest resolution eyes. We don't have the highest resolution. Falcons, they have high resolution eyes that high resolution eyes than us. It makes sense because they fly very high. They need to detect the small animals to catch them. But humans generally, we have very high resolution eyes, and we are generally proportionally we are visual agents compared to other animals. So we are skewed towards using vision a lot. Our nose and so on are not as useful that, for example, dogs and cats and many animals that are to a large part like chemical sensing, like smell a lot. So what's interesting is that there are a lot of animals that have poor vision, but in terms of resolution, but they're very perceptually capable, behaviorally capable. So like if you look at, the human and cat, fine, but once you get to the rat and fly and mosquito, it's just really hard to believe that's all they see. But if you look at their behavior, it's hard to believe that, the agile motions and everything that they have is coming from such low resolution eyes. And this is the same thing for butterfly case, but this time shown over distance too. So this is a map butterfly. This is a map butterfly sees another map butterfly only from 10 centimeters away. And this is 1 meter and this is 2 meters, almost like unresolvable. And yeah, so it's a lot, this is just 1 meter away, like this much. And this is even the bird sees it that way. So it's very poor in terms of resolution. And it's actually funny because one of the hypotheses, again, speaking of, it was that why, for example, butterflies have these patterns. Earlier hypothesis was that this could be, for example, a courtship behavior for mating. But then it turned out they don't even see it. Like the resolution of the eye is so small that they don't see it. So how could it be courtship? So it turns out it's more like for predators, like birds that have a slightly better resolution, so they see it, but the butterflies themselves don't see it. So this is more like to look like a flower that is poisonous to avoid it for the bird, but not for other butterflies. So resolution is one of the important ones too. And we'll see in Andre's talk that if you design it well, like some things that seem surprising come out of it is that basically how far can you push it? How far can you go with a very simple eye in terms of resolution, like a 1 pixel camera or 2x2 camera? And it turns out you can do a lot of embodied AI task with that, which is going to be the next talk. And so I'm going to end it here. But there's one point worth mentioning is that now that we went through these case studies and so on, it's worth remembering that animals are almost never unimodal. They always solve the problems in a multimodal way. And so when we say vision works, this is poor vision is still perceptual behavior, we have to remember that they're never almost entirely relying on their vision. So there's the caveat there. So in the end of the day, it's always like multimodal, but the multimodal aspect also has as much, perceptual morphology design to do that vision does. Common example is that you have seen is the snout of the dogs. So dogs are very reliant on their olfactory system to smell. And this thing is a very well-designed equipment. So as humans, when we want to smell, as we exhale, we kind of let molecules out. So we stop the smelling like inconvenient. So the design of their snout is in a way that there are these slits on the side. So regardless of whether they're, for example, inhaling or exhaling or any activity, they're always intaking molecules because it creates a low pressure and then it always takes molecules. So it's a morphology, clearly it's a morphology design. And snakes, their tongue is basically a smelling device. So they touch this tongue on different, they sample molecules, they bring it in, their sensing organ is on the top of their mouth, so they deliver it there. And why there's two Does anyone? Yeah,
Gradients.
gradient, exactly. So this is a stereo vision, basically. So it samples from two, so it can compute direction. So they smell in a spatial way. Again, beautifully designed. It's like a morphology problem. And this doesn't also happen only to perceptually weak animals, visually weak animals, visually strong animals, the same thing happens too. So turkey vultures usually have very good eyes because they fly high and they have to, again, detect things. But turns out they actually have very good sense of a smell too. They can detect a dead body from roughly 8 miles away. And a funny story is that there was actually a company that figured out and used turkey vultures as like a free surveillance team for gas lines. So, the gas lines are usually in the middle of nowhere. They extend for thousands of miles. It's very hard to detect like a small leakage. So what they did, they would put like some chemical in the gas that is attractive to vultures. And whenever there was a leakage, it would, go in the air, and they would basically, whenever they see vultures hovering around gas pipes, there would be an alarm that potentially there's a leak there. So the real story that they actually use these animals, that it was debated for a long time whether they have a sense of smell or not, strong sense of smell for that purpose. So multimodality is a thing, and it's not only for the perceptual, visually weak animals. Okay, with that, I'm going to hand it over to Andre for doing a design with two of the parameters that we discussed. Like I said, there's not much work in designing vision systems yet, so hopefully it's going to come more in the future. But the two parameters, resolution and placement, we have one example that we can talk about. Was there any question or? So, yeah. Oh, the function of it, I'm not sure if I have read a compelling story about it. It is just known that there is two, because anatomically and there is consequences of it. For example, when they want to land, when they are hunting, when they want to land, they go in this spiral fashion because they can keep one of the phobias focused on the target, and they kind of go around it. And that, because of that 45 degrees, it kind of leads to these particular flying patterns. I don't know if it is exactly known, or maybe I don't know exactly why they have it, but anatomically they do. And they're not rare, actually. Multiple, flying hunting birds, they have it. But... Cool.
Yeah, I think there's one more question.
Oh, yeah. Yes.
So one difference between nature and technology is that nature custom builds its components for each instance of the animal, whereas with technology you tend to have mass produced common components.
Yeah.
So is the idea here, obviously we're trying to learn from nature how to optimize technology, but is it really a matter of selection amongst maybe a finite set of things that already have economy of scale? That you'd actually have fully custom sensors.
So your question goes into basically how we should parameterize the design space in a way that is manufacturable and has, so for example, in 3D printing, that thing is incorporated. You cannot just imagining a solid 3D shape doesn't mean that you can necessarily print it. So in the 3D printing planning algorithms, that is included that you have to satisfy additional constraints. So the idea here is that like this is all at the research level. So really fabrication and manufacturing hasn't really been part of the problem yet. In Andy's stuff will be, so in the mechanical morphology, with perceptual, we are not really there yet. But in the end of the day, it comes down to kind of augmenting the design space in a way that it becomes practical, but it goes through the same pipeline. It's more like a design space that has additional constraint versus less constraint. So the example that I have for, voxels, you can 3D print. So the problem is not that we shouldn't design, because our manufacturing process enables that level of flexibility already. And similarly for perception. So the examples that Andre will talk about is like placement of the photoreceptors. There's a sensor called photodiode, which is basically a photoreceptor. So there's no problem actually implementing it as of today. The problem is like how to actually find the design that actually leads to work. Thanks.
Hello everyone. My name is Andrei, and I'm going to talk about our recent project on solving vision tasks with simple photoreceptors instead of cameras and how to design them. And I'll try to go deeper into details and specifics during this talk. So yeah, let's start. In computer vision, usually when we solve vision tasks, for example, like a visual navigation, we use a pretty standard recipe. So we use a high-resolution camera, and we place it intuitively on an agent, and then train a deep learning system to solve different types of tasks from this high-resolution signal. And as we saw, as Amir discussed in the previous talk, right, in nature, we see a wide variety of different designs. They vary in like pupil shape, the type of the lens system, resolution, light intensity, and many more. And so in this work, we focus on two specific aspects of this visual sensor design. So first, we draw the inspiration from various examples of extremely simple eyes. So many animals have rather impoverished eyes in terms of their resolution, yet they're able to exhibit rather complex behavior and survive in their environment. So what we do is we basically ask the question, how far such simple eyes can go in terms of solving some of the vision tasks. So, and we basically replace the standard camera sensor with a simple photoreceptor sensor with resolution as low as 1 pixel, which is less than 1% of the camera resolution, even for such a low resolution camera of 128 by 128. And yes, here are examples of visual signals coming from a camera and two photoreceptors that are placed on an agent embodied in an environment. So we then consider some standard active vision-based tasks, for example, a visual navigation task, where the goal is to navigate to a target ball here in an unknown environment. And we ask whether agents equipped with such simple photoreceptors can solve this task reasonably well. So second, we draw inspiration from various eyes designs in terms of the field of view, like in between predators and prey, placement and orientation of the body, like in the scallop example. And we therefore explore the role of the design in the effectiveness of these simple sensors. And we also develop a computational design optimization method to find well-performing designs. So let's start with the first question. And our first task that we consider is a visual navigation. So the goal here is to navigate to a target denoted by the star, starting from a random position in an unknown environment, denoted as a pin. And we use a data set of real scans of real buildings, the Matterport 3D data set, and we split it into train tests and evaluate only on novel scenes. And we consider two standard instantiations of this visual navigation task. The first so-called point goal navigation, where the target's position is conveyed to a robot, to an agent, via its position in the scene. And the main task here the agent needs to do is to efficiently avoid collisions and navigate as fast as possible to the target. And the second situation is the target navigation, where the agent doesn't know the target's position, but it's specified visually by having a green ball in that position. And during the episode, the agent has access to a visual signal that comes from either a camera or photoreceptor sensors. And also, as per standard practice for this task, we provide a GPS plus compass sensor, which provides a position and direction of the agent during the episode with respect to the start position. Okay. So, and now how do we actually implement a photoreceptor sensor? And in our experimentation, we use simple models that allows us to implement it in any simulators that has access to a rendering engine. So for a photoreceptor placed on an agent in a simulator, we first render the corresponding camera view with the same intrinsic and extrinsic parameters. and simply average it spatially to get the corresponding photoreceptor signal. And when we increase the number of sensors, we can either spawn a different sensor in a different location and repeat the same process, or we can arrange them in some form of a grid sharing the same location. Like here, for example, the 4 photoreceptors are arranged in by 2 grids. And then we split the image into patches and average each of them to get the corresponding photoreceptor observations. And so one can simply think of it as a very low resolution camera of 2 by 2 in this case. Yes. So here we show an example of a photoreceptor-based agent executing the target navigation task in a known environment. So it has access to 32 photoreceptors, as we show here on the left. And on the right, we show the corresponding top-down map during the episode. So, and we also show the camera view just for visualization. The agent doesn't see it. So we can see that the agent can successfully detect the target and navigate towards it while having access only to this low resolution visual signal. So, and now we show the quantitative evaluation. So we show the performance of the photoreceptor agent, like in blue, for varying number of photoreceptors. The y-axis shows the performance on the task, and the x-axis shows the number of photoreceptors used. And we arrange them, in this case, in a grids of 4 by 4 or 8 by 8, having either 2 or 4 sensors. And to contextualize these results, we employ 2 control baselines. So the first one is a blind agent, and this agent doesn't have access to any visual information. And it simply learns about the biases and the structure of those scenes from the training data. And as a visionless system, it provides a lower bound on what we would expect a vision-based system to achieve. So second, we employ a camera agent, which is basically a standard approach to solving these tasks using a high-resolution camera sensor. And we show the same for the point goal navigation task. And basically what we find in both cases is that even a handful number of photoreceptors with the resolution as low as 32 or 64 is enough to solve those tasks significantly better than the blind agent and having a comparable performance as a camera agent, and sometimes even outperforming that. So note that like this camera here, baseline, it's actually using a relatively shallow transformer architecture that we use for the photoreceptor as well. So here we also report, yes. So here we also report the more stronger baseline with the ResNet 50 architecture, which is more commonly used in this for these tasks. And we find even that compared to this baseline, right, the photoreceptors perform reasonably well. They close most of the gap, right, between the blind agent that has access to no visual information and the stronger ResNet 50 camera baseline. So here we show some qualitative examples. These are trajectories of different agents in the point goal navigation task. We show them for blind, photoreceptor, and the camera agents. And yes, as before, the start position is a pin, and the agent needs to navigate towards here. And we also display the collisions with walls and other obstacles as the red points. So what we find is that photoreceptor agent is able to utilize its low-dimensional visual signal rather effectively to avoid collisions and find much more efficient trajectories compared to the blind agent. And it achieves overall performance similar to that of a camera agent, which has access to a very high-resolution visual input. So, and similarly, we show trajectories for the target navigation task. And since here the target position is unknown, here the scene exploration plays an important role. to be able to successfully detect the target and navigate towards it in a limited number of steps. So here we show multiple trajectories for each agent, and the darker door corresponds to the points early in the episode and lighter ones later during the episode. And so what we can quickly see here is that the blind agent, for example, it isn't able to explore the scene much. So all the dark points are just around the start position. Whereas the photoreceptor can efficiently explore most of the scene and overall achieve success rate similar to the camera agent. And next, to see whether in this target navigation task, the photoreceptors agent can indeed detect the target and it doesn't like simply bump into it, we designed this very simple control experiment. So for the same episode with the same start and the end position, we create two scenes. In one scene, we have the same like visible target. The target is visible. And in the second control scene, the target is invisible. Basically, there is no target, but it needs to go to the same place. So, and we run the same photoreceptor-based agent in both those scenes. And before, they have the same trajectory before the target is first comes into the field of view of the agent sensor. And after that, the agent with a visible target in the scene with a visible target can successfully navigate towards it. Whereas when the target is invisible, it fails to do so, which basically suggests that the photoreceptor agent can indeed use this visual information about the target, detect it, and navigate towards it. So, and finally, like even though we use counts of real world in all our of real world apartments in our experimentation, we also try to see whether those observations are somewhat specific to the simulator or those apartments, and whether this can be transferred to a real world. So we attempt to study this with this simple real world experiment. So we deploy a photoreceptor policy on an turtlebot agent shown here, and it needs to navigate to this pink target ball over the box. So, and we equip it with a single 8x8 sensor with 64 photoreceptors. And here we show the corresponding camera view just for visualization. And we train the policy in a simulator and directly deploy it on the robot without any real-world fine-tuning. So yeah, so here we find that it can explore the scene and it can detect the target here, I guess. Yeah, here it goes. It can successfully detect the target and navigate towards it. And this is, of course, like a successful example. And of course, it's not 100% successful all the time. But we definitely see a non-trivial behavior of it exploring the scene, detecting the target, and navigating towards it. Yes. So, finally, we also evaluate the effectiveness of this photoreceptor sensor in continuous control tasks from DeepMind control suite. So we use the Richer, Walker, and Figure agents. And we solve these tasks solely from the vision signal. So as before, we compare the photoreceptor agent shown in blue with the blind shown with gray and the camera baseline. And as before, we see that in these cases, like just having a few or 2 or 4 photoreceptors, yeah, 2 or 4 photoreceptors can be enough to solve those tasks meaningfully compared to the camera agent. And this example shows like a walking task solved by a photoreceptor agent. So here we show the design. Each color, like these arrows correspond to each photoreceptor. There are 4 of them. And this design was found by a computational design method, which we'll describe in a few moments. So this shows the corresponding observations for each photoreceptor. So here each row shows the RGB values recorded by the photoreceptor. And this plot shows the luminance signal is just a reduction of those RGB values into a single number that shows the lightness, just for visualization purpose. And this is a reward function. It's not seen by the agent. And this is a side view. So yeah, so as we can see, it is able to successfully control its body based on just this 4-dimensional visual signal. And what's interesting, we also can know that like, even though at every point in time, we have only like a 4-dimensional input, which might not tell much about the world state and the joints position of the agent's body. But over time, over some period of time, we can see that there is a non-trivial like patterns, like for example, oscillation that correlates to the movement of the legs, which might provide actually useful information to solve this task. Yes. So these previous results suggest that even simple photoreceptors can in fact provide useful information to solve those vision tasks. And now let's address the second question on the role of the design. So, and first of all, let's clarify what the design specifically here. And so we consider the following parameters. First is the position of the photoreceptor, the orientation, and its field of view. And we denote all these parameters by theta. And yeah, there are other parameters we don't consider, but could be interesting also to explore. Is, for example, non-uniform resolution, mimicking acute zones found in different animals, light sensitivity, and like frame rate. Yes, and now given these designs, how we can actually choose design from this design space. And we consider the polling approaches. First, it's just sampling them randomly, like a random design, uninformed. Second is a computational design coming out of design optimization that tailors the design to its particular agent morphology, the environment, and the task it needs to solve. And finally, we explore how easily those photoreceptors can be designed intuitively. So first of all, given all this design, let's see how much it matters actually to have a good design for the final performance. So on these plots, we show with each dot like a performance of a given design, and we scale them to the range of a blind agent corresponding to 0 level and the best PR for that task. And we actually see that in all of the cases, the performance of the agent varies widely for different designs. And the poorly designed photoreceptors can lead to the like blind agent performance that has access to no visual signal at all. And which suggests basically that we need a computational way to design those photoreceptors to be efficient, to be effective. Yes. So yeah, how can we find those well-performing designs automatically for a given agent morphology, the scene, and the target? So let's start with a simple like reinforcement learning observation action loop. So the simulator outputs an observation, and based on that, the policy predicts the next action, and so on. So after the episode ends, after multiple actions, we get a reward function and the corresponding objective function, which we'll use to update the policy weights to improve it. And in this framework, the task, for example, target navigation, would define our objective, and the scenes, like the environment, and the agent's morphology would be used by a simulator to model physics and produce the corresponding action observations. So now, in the case when we change the design, the simulator and the renderer also depends on the visual design that we employ to produce the corresponding observations, which make them dependent on the design. And the whole process now depends on the design. And the reward that we achieve at the end also depends on the design. And the goal of design optimization is to maximize this like utility function, right? And this essentially results in a B-level optimization, where in the inner loop, we optimize the policy to work the best for a given design. And in the outer loop, we update the design to improve the performance of the policy. And a standard approach could be, for example, use a Bayesian optimization or an evolutionary search. But those would be prohibitively expensive. For example, training a single navigation policy can take up to 1 or 2 days. So instead of that, we model the design as an additional design action, which is then used throughout the single rollout while the renderer to render the views during the control actions. And then we also condition the policy on the design so it can implement different behaviors based on the current design. And now our objective depends on both the design parameters and the control parameters. And we use it to jointly update both the design and the control at the same time. Yes. So now let's look into the effectiveness of this design optimization method quantitatively. So we run optimization for each of the tasks we described before and measure the design performance before and after optimization. And therefore, one design optimization run corresponds to a point on this scatter plot, where the x-axis shows the performance of the initial random design. Okay. Do you hear me at the? Yeah. That's okay. I don't know. Okay, I'll be loud, I guess.
Oh,
Okay, it's back.
all right. It's probably the speakers.
Yeah, so the x-axis shows the performance of the initial random design. And so, for example, this is a visualization of it in this case, and it will choose the reward of 200. And the y-axis shows the performance of the design, of the computational design after the design optimization. And here is the corresponding design, which achieves a much higher reward. And while this design might look kind of unintuitive to us, there is a certain structure to it, which allows us to achieve actually this higher reward. So here the same example of before and after for a target navigation task and for the point goal navigation task. So this is an example of a optimization trajectory during the design optimization. So one interesting observation that we found that for the point goal navigation task, usually one of the photoreceptors tend to go on the bottom of the agent. And one potential explanation could be that since the agent knows the target, so what it needs to do is actually avoid collisions, which might be easier to do if you have sensor down there so you see what's happening on the ground directly. So, and these are basically results for all the tasks for all different number of photoreceptors. And we find that in most of the cases, the design optimization improves the performance, which in fact allows us to achieve performance similar to the camera agent. Okay. So yeah, we also apply this design optimization method to optimize the camera design. And we find that compared to the intuitive, like a default design employed by the simulators to solve these tasks, we find that the computational camera design can actually significantly improve the performance of these agents. Yes. And here are the examples of these camera designs. So this is an intuitive standard design. And here's a point for the example, point goal navigation and for the target navigation. So as we discussed, like similar to the photoreceptors, where one of the photoreceptors usually end up being on the bottom, we find similar trend for the camera. And for the target navigation, it stays up. And actually, in the target navigation, the target, the ball, is above the ground, and it's actually around the middle of this height of the agent, where we see the camera converge to. So, and finally, we explore whether it is easy to design photoreceptors intuitively, and we collect intuitive designs by running a human survey. We evaluate those designs and compare them with a computational design for the corresponding configurations and tasks. And so what we find is that in most cases, computational design ranks among the best designs. And what's also interesting is that performance of the intuitive designs varies widely in all the cases, which suggests it might not be an intuitive problem to solve manually. And it again calls for a computational approach to the design optimization. Yes. So to conclude, like in this project, we first show that even simple 1-pixel photoreceptors can be effective to solve different vision tasks. Then we also show that their design actually matters for their effectiveness. And to find good, well-performing designs, we develop a design optimization method that can find them automatically. Yes, thanks for listening. And I guess we have time for one, two questions.
If there's, yeah.
Mm-hmm. Yeah.
So, I mean, so when you have a low-res camera, it's you so that you can do super resolution. In other words, the receptive field of each pixel will be less than the square that you did. Over time, you can recognize higher resolution. As you rotate, for instance, you can recognize higher resolution angular signals because the camera's in. So did you experiment with different functions for each pixel? You used the square, which is sensitive, which is one thing to use the Gaussians and overlap. Sensor where essentially have narrower field of view than the sensing between them. And the networks. That's not what's
Yeah, so basically, if I understand your question, it's about like having a non-uniform resolution, right? Spatial
pre-filtering. So you can either have a limited signal like the 32 photosensor array, or you can be sharp signal that is the single image, but because the cameras so they actually jiggle the sensor over time to capture high resolution signals. So I was wondering if that was the degree of freedom you could optimize. It might give you the ability to recognize finer details, even with a small number of sensors.
Yeah, okay, yes. So we didn't directly like optimize for that, but one of the design parameters, right? So I guess I can see it here. Yeah, so it was a field of view, right, of the photoreceptor sensors. And it basically resembles, right, about what you're asking. Like, for example, if you have a low field of view, it means in the limit, right, you have a pixel camera, basically, right, that shows that like a very narrow point. And basically, for example, this is a design that I found for the target navigation task. And it looked something like a narrow. It has a narrow field of view, so it's like a very precise information. Whereas for the other task, we found that the field of view, it basically integrates a larger portion of a scene, right? So it's more like a blurry. So it was a degree of freedom in terms of like field of view. Yeah, but I think maybe exploring some more free-form structures here could be interesting. Different forms, as you mentioned, right?
Okay, example. Do you try pressure sensors instead of light sensors? simulation to see if that would help you detect.
Mhm.
signal conversion.
Yeah, so we didn't try that. We solely solved them from the visual signal. I think in a standard, like in this defined control, right, you have those. I'm not sure about the precious sensors. I think they do have them. But I think the standard approach to solve them from the world state, from the proprioception, they might have it there. And yeah, usually you can solve them pretty well using the access to those like pressure or joints, jet joints, exactly. Yeah. And here, yeah, the idea was to see how much we can pull just from the visual information, which can actually provide, right, those types of signals.
Is the question quick? Because the next speaker, we are running a few minutes.
Yes, it's not so.
Okay, so let's take it offline if you don't mind. Great.
So,
So if you can, so
so I stop sharing.
yes, please. And Sonki, do you hear us?
Yes, I hear you.
Great. And we have to now move you to the room.
You open, so first share the screen.
Yes.
Should I share?
Yeah,
Do I
can you
share my
flash it?
screen?
Yeah.
Okay.
I'm gonna exit the.
Oh. So remove this there.
Okay, so do you see a slideshow?
I believe so. We are moving it to the bigger screen, so it can bear with us.
Okay. Yeah, you'll see 3 transparent octopi on the top if you have it.
That's correct. What?
I'm sure how to move it. I guess we want this, right?
Yes.
Is it big? So we don't.
It's good. So let's do the audio. Which one is your?
Hmm?
How do you change audio? These symbols are different from mine.
No, I think we should go to Zoom.
Do you need me to talk for a moment so you can check audio?
Actually, right now we are. The moment we switch it, they'll ask you to speak.
So can you say something?
Okay, 1, 2, 3, 4, 5.
Oh, this is.
Can you check it for? Yeah.
Can you say something?
Yes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay.
Reasonable. So hi, Sonki, thanks for being here. And so unfortunately, there's no camera facing the room this year, so you don't see people here, but we're eager to hear you. So in interest of time, I'll shorten the introduction because, well, I described Sonki's work works in the beginning of in the intro part of the talk that I gave, and we're happy to have him. He's a professor of biology at Duke. And formally, I would say that, his background, he actually has very interesting material, not just in popular scientific press, but, in Finding Nemo, for example, he has contributed to it. But I'll just tell you my personal, introduction to him is that I have actually used a lot of his material in terms of getting inspiration, in terms of diversity of vision and adaptation to ecology. And not only have read him directly from his talks and so on, but what was interesting is that many of the books that I read, that they were bestsellers, such as Ed Yong's An Immense World, actually used his material. So I indirectly also landed on his material very well. So we're very, very happy to have him here today. And all the, and earlier we saw in the introduction talk that the diversity of biological vision is a great motivation for everything that we're discussing today. So Anki, the stage is yours.
Okay. Thank you. And thank you so much to the organizers for inviting me. I'm really happy to be here. I'm hoping you can see the screen well and hear me well, because I can't get any feedback from you, so I'll just have to know that you're out there listening. I'm a little bit unusual among a biologist in that I actually come from a math and physics background, in addition to the visual arts. And so very early in my biological training, I became enamored of all the visual properties of animals and their visual systems. So I've looked at, a number of different eye designs, ranging from eyes the size of soccer balls, down to microscopic eyes that are made out of different inorganic materials and so on. Looked at iridescence, transparency, ultra black coloration, ultra white coloration, mirrored objects, camouflage signaling, and in a number of different habitats, though I'm particularly interested in the open ocean. The techniques we use are all over the map, literally, in that, we travel in oceans all over the globe. We do open ocean scuba diving over depths of about 3,000 to 4,000 meters. We lower a lot of different kinds of optical measurement equipment into the ocean. We go down in submersibles. We develop a lot of cameras that, can, let's say, see polarization or some other interesting sort of thing. And we do lab work on molecular biophysics, different sorts of materials characterization, and a fair bit of mathematical modeling and different kinds of imagery. I was asked to give this talk quite recently, and it had a particular sort of length. And so this is one of the talks that happens to fit that well. And I think it will actually work pretty well for this conference, which I did attend a number of years ago in Pittsburgh. And so at least I have some idea of, what you might be interested in. So this particular talk is about eye design. As you can see from this nice little splash screen, eyes relative to body size vary all over the place. Eye designs, there are animals with multiple retinas, animals with mirror optics instead of lens optics, animals with extraordinarily low f-number lenses of about f-number about like 0.4, animals with tubular eyes, and animals that have eyes of different types depending on which direction they face, so they can optimize viewing for different viewing conditions. And it's typical among people in my world that study comparative animal vision to become very enamored of color. We're all very interested in color. It's very pretty. And, there's always the temptation to feel that you can see something, one animal can see something another animal cannot, and that there can be secret channels of information and so on. But you're immediately pinned in by the fact that the visual range in the electromagnetic spectrum is actually quite narrow. Really only about a factor of 2 of wavelengths, are really there for you to deal with. The maximum sensitivities of visual pigments only get up to about 630 nanometers. The minimums get down to about 350 nanometers. And within different groups of animals, you find that there's a lot of what we call, evolutionary conservation in terms of variation. If you look in the upper left-hand corner of the birds, you can see that, for their different classes of cones, there's really very little variation. And so there's not as much to play with, to think about how different animals see the world as you might hope. In addition, as I'm sure you're well aware, being a computer vision group, not that much information is coded in the color channel. Here's, just a simple image from Duke Marine Lab at top. And at the bottom, there's a black and white image, and you can see that you can pretty well make out everything. This is why black and white TV, of course, works so well for so many decades. The middle image gets rid of the luminance channel and presents only the color channel. And you can see immediately that, any sort of three-dimensional rendering is very difficult to pull out. And the color is really only good for identifying details. If somebody's wearing an extremely red coat, or if a boat is blue, you're able to pick that out, but you can't really use color alone to parse out a scene. And so we became interested in spatial vision, and the differences of acuity. And here among animals, the differences of acuity, even among animals that you would normally consider as having eyes, is enormous. We're near the top with acuity of about 100 cycles per degree. A few eagles beat us out, but not by much. And then it goes down by about 4 orders of magnitude until you get to insects that we normally think of as actually having fairly good vision, but their acuities are only about, let's say, 0.1 cycles per degree. In fact, most of the visual world of animals is in what we would call, legal blindness by human standards. And so when you look at, the world from their point of view, it's actually dramatically quite different. If you look on the left here, there are some beautiful little cleaner shrimp, noted for their gorgeous color patterns on their body. Interestingly, these animals do not have color vision at all. They only have one visual pigment. And so the middle column is showing what these animals look like to each other. And, of course, you can see there's almost no information left, of course, about the color being monochromatic. But then you step to the right, column, and you see what they would look like from only about 3 centimeters away. It turns out their visual acuity, even though they are quite visual animals, is only about 0.1 cycles per degree. And so even at very close range, a static image provides almost no information. A moving image would, of course, provide more, but you can see that at the very least, all the cute little patterns that they have on their body are gone. And so we work not in these, sort of shallow water habitats, but we're very interested in the open ocean. And we're particularly interested in how vision has adapted to work at different depths. And as soon as you get into that puzzle, even in very clear water, you're dealing with the trade-off between sensitivity and resolution, just as you would with a camera. Basically comes down to pixel size, though the different animals control their pixel size in different ways, quite differently than we would control with a camera, and quite differently from each other. And so you can go from, a very dim and sharp image to a brighter and fairly blurry image, sort of balancing out these two. You can increase both, of course, by making, the eye larger, just as we can make something larger by making the sensor larger. But even though, the neuronal system has a wonderful ability to amplify signals, the quantal nature of light, as you well know, gets in the way. As you get dimmer and dimmer images, the signal of noise increases due to photon noise. And so you can't take a dim image and just amplify it and get a good image. You end up with just a lot of sort of noise. And this was the problem with the early iPhone cameras. They were wonderful during the daytime and truly terrible the rest of the time. So the final thing to think about before we get into sort of the calculations about this is that when we think in the ocean, we mostly think about 2 different kinds of light fields. We think about animals that have what we would call extended vision, seeing under ambient light, seeing, basically a spatial description of the world. This is a nice picture here of a poor collection of bait fish being eaten by both birds and sharks at the same time, which is not uncommon in the open ocean. And particular eye designs work particularly well for resolving the world under ambient light and developing, a nice spatial, pattern of it. Many animals in the ocean, though, especially once they get deeper, are really living in a world of point sources created by bioluminescence. And then pretty much all the identification they do is by the spatial temporal patterning of these point sources. What you're seeing here are bioluminescent ostracods, where the different species will move through the water column in different patterns, such as a spiral, straight line, changing directions, and also emit light at certain periods in that, creating a sort of spatial temporal point source dance that allows them to be identified to species and allows other animals to then show up and mate with them. And this requires a different sort of eye design that, is successful for that. And so to give you again, why the world in the ocean changes, especially as you get deeper than about 500 meters or so. This is based on a model, I won't go into the details of it, of how far away an animal can be seen that's about the same size as a viewer divided by body size. So 1 would mean that a 2-meter person could see a 2-meter object from about 2 meters away on the x-axis there. And what you're looking here is a number of different squid species, each sorted by the average depth that they live in. And you can see that once you get to about 500 meters, the ability to see things really starts to catastrophically drop. You get to, sighting distances are only about a body length or less than a body length, and eventually down to many, many orders of magnitude less than a body length. Just for fun, we worked out how big a pupil would need to be for an animal at 1,000 meters to see as well as we do at the surface, and it would have to be about 1 kilometer across. However, once you introduce bioluminescence, even if it's quite dim, too dim to be seen, even in dim room light, such as you're probably sitting in right now, the ability to see over decent distances is recovered, and they're able to see things at about 10 to 100 times their body size, even working with a small amount of light. So even very clear water, this is water from the Bahamas in the middle of the day, clear, sun directly overhead. Even with that amount of light, a few hundred meters of ocean can just drastically reduce the amount of light available, which makes it a nice natural laboratory for looking how animals balance out sensitivity and resolution to maximize, their ability to see at those depths. What's going to follow here is a relatively simple model to sort of look at what would be essentially the best acuity as a function of depth. How would an animal best balance acuity and sensitivity to be able to see things the furthest away? And so you have here a squid looking at a striped fish. It not only wants to be able to see the fish, it wants to actually be able to resolve the stripes, which have, a length of S for one black and one white stripe together, a distance D. And the first thing that you have to deal with, I'm going to sort of increase the complexity of this model as we go, is you have to deal with the modulation transfer function of the eye. And as, an animal, this target moves away from the squid, it's going to become more and more difficult for the stripes to be made out. At the moment, we're not even considering the water. Nicely enough, the modulation transfer function of the eye has been measured a number of times in different eyes. It is a relatively common feature that can be determined almost entirely by what we call the resolution of the eye, which we can work out using both behavioral and morphological techniques. It is this delta rho, and it typically follows something not so different from a Gaussian, which you see here, with a particular gamma. And so using this, you can then, in theory, work out, how far away, an object, these stripes can be seen as the contrast drops due to the modulation transfer function of the eye down to the contrast minimum. However, it gets more complicated than that because the minimum contrast threshold itself depends on how much light is entering each pixel, because you're dealing with a fair bit of noise as the light levels drop. It turns out the light levels drop enough for each individual pixel of this eye, this collection of photoreceptors, such that the signal to noise ratio just from the photon noise itself ends up being quite low. And so based on the fact that photons enter and interact with matter in a Poisson process where the standard deviation is closely related to the average, you can then work out what the minimum contrast threshold would be. And it's essentially a function of the resolution of the eye and the amount of light that enters the eye, which is just a function of how much available light there is and the pupil size and so on. You put that all together, you can actually very simply analytically work out what the sighting distance would be as a function of light level, the resolution of the eye, the contrast of the original target, and so on. And as you might expect in a world where an eye with one pixel would more or less be useless, and an eye with an infinite number of pixels would also be useless, and sighting distance always has to be a positive number, somewhere in the middle there is a maximum. And you see that here just for a number of different light levels at different depths. You can see that as we change the resolution of the eye, the sighting distance goes up, and then it begins to go back down as, and where that Mac is a peak is where we have sort of the optimal balance of resolution and sensitivity for that particular set of parameters. The problem, though, is that you also have to consider the water itself. All these calculations were essentially done in a vacuum, so you have to consider the modulation transfer function of the water, which has two components. It has a frequency independent component. You can think of sort of as scattering, the veiling light, and that can relatively simply be calculated using sort of adaptations of old ocean optics, papers back from the visibility lab at Scripps, back even as far back as the 50s from Preisendorfer and Duntley and so on. And then you also have to deal with multiple scattering, which is a frequency dependent effect. That has, thank God, been actually worked out by Ron Zandeveld and Scott Pagel a number of years ago for the types of waters we're interested in. And so you can put all that together. This cannot be solved analytically like the earlier equation could, but it can be solved numerically, relatively easily to work out what is the optimal acuity for an animal as a function of the contrast of what it's looking at, the size of the stripes that it's looking at, how much light is actually entering the eye, which depends again on the pupil and the optical qualities of the water and the depth and the time of the day and the integration of the time of the eye and so on, and the clarity of the water, which actually has a fairly large effect, as you might guess, here given as the beam attenuation coefficient of the water. We then had to pull together, because we wanted to be able to compare this model with reality, we pulled together what were the acuities of quite a number of different fish. For those of you unfamiliar with this, the tree-shaped structure on the bottom is showing the evolutionary relationship between all these fish. You can see actually that there is some connection between the evolutionary history of a fish and how sharp its eyes are, but it's not as simple as that. We also looked at sharks. Sharks on average have about half the acuity of the fish we are looking at. It's actually kind of interesting. The sharks mostly go around, even though they're quite large, with quite blurry vision. Normally, large eyes are actually quite a bit sharper than small eyes. And then we just compare this, to the model. The model are the different colors of smooth lines. Models are always, nice and smooth. Here, we're just looking at, what are the predictions for different levels of stripes. The optimal acuity depends, of course, on the size of the stripes you're dealing with. And what we found is that for animals at depths less than about 500 meters, in that what we call the ambient light range, the predictions of the model match what's actually seen in the animals within about a factor of 3, which for biology, which mostly lives in the land of one significant figure, isn't bad. We never get, accuracies of 5% or 10%. Typically, we're trying to get within, 50, a factor of 2 or 3 or so. But what you see is that as you get below 500 meters, the actual measured acuity of these animals is dramatically higher than what is predicted. These animals have much, much sharper vision than you would predict from the models. At those depths, the prediction of the model is that the animals should sacrifice nearly all of their acuity to be able to see as well as they can, but instead, they have much, much higher acuity than you would think. This is just looking at the model on a different sort of slice through the parameter space. Here, we're actually changing the clarity of the water. The sea and open ocean water, for reference, is about 0.05. We again see, about the same effect, where to depths of about 500, 600 meters or so, the model and the actual measurements of the animals are within about a factor of 3. But then when you get deeper, you end up with much, much sharper eyes than you expect. This actually follows predictions that were made probably about 10 years ago by a colleague of mine, that as you move from the ambient light realm, the top 500 meters of the world, where you're seeing under, diffuse sunlight, even though it gets quite dim, you get a very different world than when you're in the point source realm, below about 500 meters. When you're in the point source realm, all you need to be able to do is know where the point source is happening, leads to quite different principles, and you end up having eyes that in reality are actually quite a bit sharper than you would expect, because all of the light just sort of falls on one photoreceptor or one small group of photoreceptors anyway, and you're not worried about the F number of the system and so on. So in conclusion, even a small amount of light attenuation in clear water. So in these depths, the water has a visibility, believe it or not, of about 100 meters. It's extraordinarily clear water. It's enough to dramatically change the predicted acuity. This has a very, very large effect. For species at daytime depths, less than about 600 meters, you are able to work out the balance between acuity and resolution to fairly accurately predict what the animals are actually doing. And so it does look like, they're working to optimize their ability to see things as far away as possible. But once you get deeper, the measured acuity of the actual animals is much, much higher than the predicted acuity. And this does match previous predictions that very deep sea animals that are looking entirely at bioluminescent flashes work better having very high acuity to localize those flashes rather than trying to optimize their ability to see under ambient light, which at this depth is more or less gone for them. Again, just would like to thank the organizers, thank the Air Force and the Navy for funding this work, and be happy to take any questions.
Thank you so much, Sanki. Are there any questions? And if there is, you have to walk up to the microphone here. And it's okay if you, and I have one, by the way, like one question in the sense of, so most of the discussions that we had earlier today were about like terrestrial vision, the biological vision that we discussed. So I wonder, like, since you're quite an expert in this area, so other than, the intuitive thing that comes to mind, that the biggest difference between terrestrial and underwater would be the distortion of light, like, and darkness that would be caused by water. But is there like another characteristic difference between the two that is missing in your opinion?
Yeah, well, there are a number actually. So, one, of course, is, the tremendous change in light level with depth. Another is the tremendous change in both light level and spectrum, depending on viewing angle. So that when we look in different directions, it doesn't necessarily change, the quality of the light entering our eyes. Of course it does if you're looking at like something on the ground, but imagine, let's say, a bird in the air, whether it's looking horizontally or at a 45-degree angle or, further up towards the zenith, things don't change that much. But because of, the water, interacting so strongly with the light, there can be an enormous difference depending on the viewing angle. Another difference, of course, is that the spectra of light are dramatically affected, even, on top of, the light level changing. And that is also affected by viewing angles. So if you're in the open ocean and you're looking down, the upwelling light is purple, the downwelling light is close to white, and the horizontal light is blue, which has a big effect on eye design. I mean, there are a number of animals, like I mentioned, that will have one eye looking up that's completely different than the eye looking down, because they're dealing with different spectra, potentially different sort of things they're looking at. Like one animal only looks down for bioluminescence and only looks up for silhouettes, and just has a completely different eye for that. The other thing, of course, you have to deal with underwater, if you're within, let's say, the top 10 meters, with Yoav Schechner has talked about a number of times, are caustics. You have to deal with the fact that the surface of the water, unless it's very still, which is rare, is acting as a number of positive and negative lenses. And so you end up with the caustics moving around and the level of brightness going up and down by several orders of magnitude over time periods as short as, let's say, a 1/30 of a second. Darius Stromsky did a fair bit of that work at Scripps, showing that particularly when you're looking up, it's extremely complicated. Both the caustics and the sort of basically the spatial temporal aspects of the caustic lensing at the surface make a dramatically difficult light field to work with. So those are sort of the main ones. The final one, of course, is that the ocean varies a great deal depending on where you are, depending on what is dissolved in it. We, have to deal a little bit with pollution. Of course, we deal with clouds and we deal with haze in the terrestrial world. But in the ocean, just a small amount of dissolved sediment, a higher amount of chlorophyll can dramatically change, the light levels as a function of depth, and also the spectra as a function of depth, and the angular dependence of light level and spectrum. And so, you're dealing with a world where very little bit of addition of materials can change almost everything that's needed to be able to see well.
Wow. I hope somebody makes a VR sort of experience for this for us to wear goggles and experience different oceans.
No, that would be good. It wouldn't be too hard because there is, unless you're dealing with very murky water, there's some very good radiative transfer systems out there that would allow you to actually work out, just based on the inherent optical properties of the medium, what the apparent optical properties are. So it would be doable.
Is there a question? Go ahead, quick one. Yeah.
Yeah, thanks for the talk. And I wanted to ask just maybe for an opinion. So it's related to Amir's question. So before you start even work out the formulas, right? and the optimal like acuity. You need to define all these variables that will be influential actually, right? And to identify the optimal acuity. And assuming those designs that we find in animals are actually optimal, how do you think far we can go by finding those variables and explaining them qualitatively on the formula level, other than employing some sort of a black box, model that takes those conditioned environments and tries to predict as close as possible, like as accurate as possible, the actual eye configuration in the animal? Um,
I'm not quite sure what you're trying to ask. What are you trying to ask?
So I'm trying to ask, like, how do you think, like, from your experience, right? You're trying to identify those variables, like the depths, right? The water, like the diffraction, and so on. From your experience, how easy you think it will be for us to figure out all those variables and work out the formulas instead of doing some kind of a black box approach where we try to.
How easy is it to measure those? Well, a lot of it's known. So, I mean, I know this is, somewhat alien to your conference, but there are worldwide databases, let's say, of the big things. I mean, in the end, it actually only depended on about 4 things. It depends on what you might call the inherent optical properties of the water, which are its absorption coefficient, its scattering coefficient, and so on. And those are known globally to a fair bit of accuracy. They can vary on time of year and so on. The other parts are just, how much light enters the eye, which is a simple or the camera, which is a simple matter of the aperture and the light level available, and then some features of the target. And that's about it. So these are not difficult things to measure. The hardest thing, if you want to think about, particularly near shore waters that can be quite variable over time, that can be a trick because you can have, let's say, I don't know, a whole bunch of rain in the mountains behind Seattle, and it dumps a lot of fresh water into Puget Sound, and then Puget Sound is going to have different optical properties than it normally does because it can lead to a bacterial bloom or a death of phytoplankton or things of that sort. But the rest are relatively simple geometric parameters. So you can do something like this, like let's say you want to work out, a camera that will work best at different depths for looking at different targets. It wouldn't be too difficult to do this. There's a nice demo by a colleague of mine. He actually built a small train set, and then he, drives through it, using, the sort of the parameters you might expect, let's say, for human vision, and then adjusts the acuity so that you lose some of the resolution, but you gain sensitivity to the optimal point, and you end up, with actually not a bad image. I could actually probably get my colleague to send that along. These things actually have been adapted for technological use.
Yeah, that sounds interesting.
Is there one more question?
If you don't mind, yeah, because we are running like over the coffee break by 15 minutes.
Yeah,
so
I
it
assume
would
I'm
be
running into your coffee break by now.
Yeah. Well, thank you so much. It was great. I appreciate it very much. I'm glad that it actually worked out and you enjoyed it.
Well, good. And if anybody in the audience does have a question, I'm easy to find on email,
Thank you so
since I'm
much.
the only
Sanjay.
person in the country that has my name. So
Perfect. Thank you so much. So let's thank Songhi one more time. And we'll see you at 11 for the next session. Enjoy the coffee break. Thank you so much. Appreciate it.
of course, sure thing. Take care. Enjoy the
Sure.
conference.
Thank you. Bye-bye. I guess we'll leave the Zoom on, no?
Yeah, I guess you can just turn off the mic maybe.
Okay. I'm gonna try to pound 2 cups of coffee. Test. Test.
We do it more in terms of like more
Okay, I'm just gonna get started. Just gonna get started. This is all working fine, I think. If can people hear me okay on the Zoom? We changed computers, so oh my gosh, I'm too loud. Okay, push that up a little bit. Test. This seems okay. Okay, sorry, I'm loud. Okay. If anybody can't hear me on the Zoom, I guess just oh, okay, there's a thumbs up on the Zoom. That's great. All right, I guess I'm kicking off the second half, not the afternoon, but the second half of the morning here. So I'm going to be talking about the other side of things, everything that's not visual today. So for you brave souls who are here, I'm sorry if you wanted vision, but there'll be very little vision. There'll be a little bit of sensing, but I'm going to talk about we'll say the stack of all the capabilities that go into a computational design pipeline for designing robots. And I guess with that, let's begin. So why is this important? I want to start off by motivating why it's important to have computational design workflows. It's scientifically interesting, of course. As you saw in the morning, there was a lot of connections to ecology, but I also want to point out that the world is already full of really complicated machines that require a lot of time and energy and labor investment in order to make these things work. And they're all dynamical and they're interacting with the world around them. So they are all environmentally driven, from construction to things that we wear on us to things that might live inside of us. And increasingly, we have this demand and this dream of more and more complex machines. And so you have people pitching these days to start up VC companies and whatnot, all these crazy ideas about lab automation and manipulators and maybe even biologically organized engineered organisms. And this is all really, really exciting. And the question though is, if it's already hard to design the things on the top, how much harder is it going to be to design the things on the bottom? And what tools will we use? How will we design this future dream of ecosystems of machines, robots, and artificial life? This is especially important as AI is starting to take over, because not only are the machines themselves complicated, but also the intelligence living upon them is going to be very complicated as well. And I think that it's really important that we come up with a better way to do this, because I don't think we should be playing, risking things on critical infrastructure here. And right now, the current industrial design workflow looks something like this. You have some sort of task specification that you come up with, some sort of mission that you want to accomplish. So maybe I need a robot that can quickly walk upstairs. For some reason, you've decided this is something that you need. And then from that, you go through the following process. You spec out what are the different components that you're going to use, and come up with some sort of conceptual design. This is maybe a little bit explorative, or maybe at a certain point you might fine tune it and come down to the final working version of this thing. And then when you build it, you then have to program it. And then if you make any mistake at any point here, and you find out that the thing that you programmed doesn't work, well, then you have to go back to square one or square two. It's not always clear where. It's not clear when you should go move backwards in this cycle. And it's also not clear if you should just give up with this idea altogether if it's not going to work. We don't have certificates for any of these types of things. There's not a lot of advice in the manual process. It all comes from intuition. And that intuition has been great, but it's also led to some products that are more complex, having lengthy spiraling development pipelines. It can be slow, it can be expensive and laborious. And basically, this is trial and error-based design with a lot of intuition to guide this. Of course, what we're going to talk about today is specification-driven co-design, where you simultaneously take a sort of mission specification, and you simultaneously come up with how do you reason about all the different aspects about this simultaneously in order to come up with a design that is generated by a computer that can be fabricated and would ideally immediately work for you. That's the dream. That's what we want to sort of achieve. This is an example from a project we've worked on called RoboGrammer. Everything here, the topology of the robots and the controllers, they're all automatically synthesized without a human in the loop. So this is very similar to the Carl Sims stuff you saw from earlier. This is just taking more of a new age approach to that. Right? And I want to also stress here that when I talk about robots or cyber-physical machines, this is really a very broad range of different types of devices. So you can use the same paradigm to design robots, of course, but really anything with a body and a brain. And that intelligence that we have can be put completely into the brain or completely into the body or somewhere in the middle. So just to take as an example, if you wanted to make something that's going to balance, yes, you can have a complicated robot that learns to stand with a lot of onboard control, but you can also put more of that intelligence into the morphology of the system, make it softer, give it forelegs so it's able to balance more easily statically. Or in the extreme example, it's not really a robot, or maybe it is, I don't know, but you don't need advanced controllers to enjoy the porch. So these are all examples of systems that can balance with varying amounts of onboard intelligence. And these are all valid solutions to this problem of making something that balances. And this idea of a cyber-physical system really can range over a whole wide of different forms. So you can have things that live completely virtual and agents, or you can have something that's completely physical. And you can think of things at the material level, or you can think of things at more of the larger systems level. So these ideas will really generalize to a lot of different areas. I'm hopeful that these algorithms can be applied to more domains in the future. So speaking of those different types of domains, there's roughly 4 different types of problems that you can consider. You can think of designing for the virtual world or the physical world. And then you can also think of things where you care about just the morphology, or things where you care about morphology plus some amount of control on board. So this will determine whether or not you're working with static objects or things that are going to move, and whether or not you have to care about whether or not you can fabricate it and make it work in the real world. And these are types of considerations that are going to drive some of your decisions prior to do your computational design work. I think there's 4 main goals that you should have when you're coming up with algorithms that are going to help you to design different types of robots or different types of structures in general. So design technology, ideally, you don't want it to be very slow. You want it to be fast. Evolution is very slow. Evolution is beautiful, but we don't have 1 billion years to design new robots, or even 1 million years. So we need something that's going to work faster than that. Second, you want the things that your algorithm produces to be performant. So it should be something that gives you good designs, not things that are fast to generate, but crap. Third, ideally, you want your algorithms to be very explorative so that they give you options, because maybe you didn't define your mission specification exactly perfectly. So there's, you want to think about what other ways you can go about solving your problem. And finally, you want it to be actually realizable in the physical world. So this is sort of the problem setting that we're dealing with here today. And for the rest of today's talk, I'm going to go about introducing a little bit of theory. This isn't really a formal area yet, so to speak. And then talk about some preliminary simulation and control considerations. And then I'll get into some computational design algorithms. In the second half of today, which starts on the 5th point there, that's where we'll start more of the learning-based approaches and think about how do we fabricate and handle bringing things to the real world. If there are any questions throughout this process, of course, please feel free to interrupt me and ask questions. Otherwise, I'll jump right into this. And I'm going to wind up using a bunch of things that I've worked on to motivate a bunch of this work. And I'll try to give you guys a bunch of other examples of other work that's relevant. Just for the larger chunk of this, it's easier for me to talk about things I'm more familiar with. But there's a lot of great work out there, and I'll try to highlight some cool things as in the community. So this is my one requisite math slide. So I'm going to briefly describe from a control theory point of view how we can design these sorts of computational problems, because I think it really helps to digest some of the unique computational challenges here. So in control theory, you have some sort of dynamical system. You have some time evolution of a state that is contingent on what is your current state, and also the control inputs that are going to be sent into the system, right? So you have a system state, a control signal, and then you also have some sort of dynamics engine. This could be simulation, or this could be the real world. And then ultimately, you're trying to measure how good is my state evolution, and that's governed not only by the physics of the system, but also the controllers, right? And so this L, this loss function, determines how bad did I do in solving a task. So over time, you can imagine I want a robot to follow a certain trajectory. Okay, so this quadcopter, does okay, doesn't solve it exactly, but at least you can quantify how bad it performed, right? And then the name of the game is, can we minimize the badness of that? Ideally, bring it down to 0, have it track that thing perfectly. Because if we can do that, then we have perfect control. The catch here is that you might not be able to do that. And I would argue that the reason why you might get suboptimal results here, or maybe not be able to solve the problem that you're trying to solve, is that it's not only a matter of the controller that you have, but also the physical design parameters of the system. So we want to simultaneously reason over the controllers that the robot is going to have, the brain, as well as the physical body. Now, to break this down into 4 rough systems that you might care about here, first of all, you have a design space. This is a parameterization of your system, And this is the space over which you're going to search. So some variables that represent how you're going to get control signals, or some variables that translate, floating point numbers into some physical instantiation of a system. The second thing you have here is you have some sort of objective function or some sort of cost. This is a mathematical function that is going to essentially codify your problem into mathematical terms, something that an algorithm can reason about. The third thing here is that you have an optimizer. This is your computational design algorithm, and this is something that a lot of people are, usually really, really excited to talk about. This is usually the meat of a computational design problem. But I will also note that the simulator is going to have a lot of effects as well on how you solve your problem. And the right simulators can help you to solve problems more efficiently or more accurately. Now, this is a world where I didn't need to start this video already. Okay, well, anyway. This is a world where you have three types of inverse problems that are stacked atop each other. So starting from some sort of design parameters, you're going to come up with some sort of gamut of virtual designs. This is an inverse design problem. From some sort of objectives that you care about, what is the design parameters that optimize you in your Pareto front for your objectives? Then you have a second inverse problem of, I have a virtual design, but I only have certain physical realization ability. Maybe you're using 3D printing, maybe you're using milling. It doesn't matter what it is, but you're limited to a certain set that you can actually fabricate. So you need to come up with what are some virtual designs that actually can be achieved in the physical world. And lastly, just because you can actually fabricate a design doesn't mean that it's going to work. So you need to also come up with what are the types of systems that when you try to translate them to the physical world are going to be accurate. And they're going to translate faithfully. So this is a really complex, like triply nested inverse design problem. And we're going to try to talk about as much of this as we can today. The last thing I think I want to talk about before we go on to the simulation part of this is the different types of robots that you see in the world today. There's a lot of different classes, but I would say broadly, these days, the most popular types are either rigid, soft, or some sort of hybrid. And I think that's true for nature as well. So you can think of the rigid world as things that have skeletons, right? These have a compact number of degrees of freedom. From just the joint angles, I can tell you exactly where I am. Also, if you have, my 6 degree of freedom body frame. And from that, you can reconstruct exactly my pose. But there's not a lot of elasticity in a rigid system. So that can be a positive or a negative. Usually it's a negative. And it's also skeletal. It's not deformable. That has both pros and cons in terms of the fact that if I am skeletal, I have the ability to sort of lock joints and have also easier to control system and an understandable system, but I don't have the nice deformable manifolds maybe that are useful for manipulation. And these are, the benefits of soft robotics is that you can have elasticity, you can have softness that allows you to grasp things more robustly. But of course, some of the drawbacks of this is that they're really, really hard to model. There's infinite degrees of freedom, and they can move in all sorts of crazy ways dynamically. So they do require a lot more computation in order to reason about them. So that's sort of our problem setting. And now I'm going to talk a little bit about different types of simulation algorithms. And this is really important because if you want to know if a robot works, you need to test it. And it's really expensive to build every single prototype. So you want to try to do as much as you can in simulation. And that's where that comes in and is useful. So of course, as you have different types of robot types, different types of organism types, yes, you also have different types of simulation types. There is rigid body simulation, which over the years has become very highly performant, and you can do it extremely efficiently on the GPU. This is some work from Ron Fetko's group back in, I think, 2004. So 20 years old now, and we can do this even better these days with the crazy GPUs. We have some work from Karen Wu's group back in 2012. These are rigid soft hybrid systems. You can simulate rigid walking characters, but also on their feet, they've added some soft compliance, and this can naturally help these characters to also to balance without having to put in extra work. And finally, of course, fluid simulation is very, very popular, and it's very important, especially in organisms that or agents that are going to be flying or going underwater. These types of systems, you want to be able to understand the coupling between the body itself and the environment. Really, this notion of coupling has come up at least twice here, and there's a whole area called multiphysics and multiphysics simulation engines. Packages like COMSOL and et cetera do this, especially in the statics regime. But this is, there's the coupling problem is extremely difficult, but in theory, you want to be able to simulate as many different phenomena, whether it be fluids, solids, soft materials, but also things like thermal, heat transfer and electromagnetism. These might be relevant to your problem, they might not. And you have to determine that when you pick a simulator. In simulation, we have, it's basically broken down broadly into 5 steps. No matter if you're a soft robot or a rigid robot, you have some sort of full state of the system, and then some observation of the system. That's something that an algorithm is going to be able to reason about, some compact representation. And that might be important because you might have a partially observable system, maybe because you're in an environment and you can't see all of your environment at once. Or maybe because you're a very high dimensional system and there's an infinite dimensional system and you need a compact representation. That's fed into a controller, which you're going to want to train or optimize, which then provides actuation. And then this feeds into simulation. And there really should be a substepping thing here for the people who are in the know. But then the steps to simulation. So for every maybe it depends on your system, but maybe every hundredth of a second or 10th of a second, you're going to want to do a simulation step, and you're going to have to do all these calculations. So it can get expensive, but there's a number of really trade-offs ultimately that can help you to choose whether or not you have a fast simulator or an accurate simulator. So you have to decide, what type of media do I have to simulate? Is it rigid? Is it soft? Is it high dimensional? Is it low dimensional? Do I need a highly accurate simulation, or can something coarse get me most of the way there? Do I need perfect models before I build something, before I'm confident that it's going to work in the real world? What is the dimensionality of my system? If I'm working with soft materials, it's an infinite dimensional system, and I'll try to represent that in a high dimensional finite way. So based on that, you might want to make some decisions about whether or not you want to use, for instance, GPU acceleration or something else in order to make this go faster. And of course, you care about the speed because you don't want it to take forever. Certain systems are extremely stiff, and so they take a very, very long time naturally to simulate, or they will break and they will actually numerically explode, which causes everything to go to not a number. So you also want to sometimes pick certain aspects of your simulators, particularly your time integrators, based on conditioning. And we'll talk about a few other things that you might care about very soon, which is differentiability of a system and incorporating control. And I'll talk about these very coming up. Ultimately, there's a whole bunch of different components you have to choose. The nice thing is that they're roughly modular. So even though off the shelf, you're going to pick one simulator that exists that's open source, or you're going to develop your own, a lot of these different building blocks, time integrators, state representations, even observation models, controllers, these are all agnostic to the actual physics themselves sometimes. Certain ones work better with different physics systems, but they're all plug and play. So you can swap things out usually according to what you need. Okay, now I mentioned that not also that there's something called differentiable simulation. So all models are wrong. Some are useful. Some are particularly useful. Some simulators, you can get more information than just a certificate or an evaluation of how well a system is performing. So I'm going to talk about a project we worked on called Chain Queen. This is a fast, accurate, by which I mean physically based, and differentiable simulator. And by differentiable, I mean that any output of the system can be efficiently computed with respect to any input of the system. The gradients of any output can be, the gradients of any output of the system can be computed with respect to any input of the system. And that's usually smooth and fast. Those are two things that you want to care about for this to be useful. So you can think of this as a simulation as a neural network, really long, complicated, nonlinear function. And what we want to be able to do is, like a neural network, also be able to compute gradients of that and be able to optimize different parameters of that simulation. Those parameters can correspond to the physics of the system, or they can correspond to parameters of your design. So to go through this process really briefly at a very high level here, if you have a task such as, I want a robot to run forward as far as possible in a certain amount of time given, well, from my physical design parameters and my control design parameters, I can use the physical design parameters to instantiate some sort of robot design. And then I can use my controller that I have here in order to time step the system forward. And it hops forward very happily. And eventually, we can evaluate how far forward did it walk over a certain amount of time. Now, maybe it didn't do so good. That's okay, because we can then do backpropagation through the physical simulation itself and compute the gradients both with respect to the controller and the design parameters simultaneously, updating it and allowing it to optimize. And this is agnostic to the simulators that you use, and I'll highlight a few differentiable simulators later. But I'm going to use a soft robotic simulation here. It seems to be a little bit more amenable to having smooth system outputs, even though the drawback, of course, is that they're very, very slow to compute. So I'll show you how you can use this for control optimization. So for a pure control optimization problem, for design variables, you have, and I guess we're sort of leaking into the controllers section of this talk here, but let's just go with it. Neural network weights. So we have a neural network that takes as input some sort of representation of the state of the robot, and as output sends actuator signals to these red and green chambers. And I'm sorry it's not super colorblind friendly. I wish I could go back and re-render these videos. So these actuators signals will actually cause these chambers to contract or expand, and that's going to allow you to move the system forward. So we just have 4 outputs, but we have maybe, you know, if we use a low dimensional representation of the observation, like 20 inputs or so. So this can lead to a neural network if it has 2 layers, 64 neurons. We're talking about maybe a few thousand network parameters. So it's not a small problem. It's not a huge problem, but it's pretty big. And just using Atom as an optimizer, we're going to show you how you can use this to do control optimization of the system. So one thing that I want to note here is that you can get these simulations to be really, really fast by using a GPU. So every gradient I show you on all the systems I think that I show you today, the simulation plus the gradient calculation, no more than 15 seconds. And for some of the simpler systems, it can be a half a second long. So for something like this is going to show you the time evolution of this soft robot as it's learning to walk forward. Really just after, after about 12 iterations, it really starts walking forward pretty well. And if that's 0.5 seconds per simulation and gradient computation, and all that we're doing other than that is doing a gradient update of the system, then what you have is a robot that learns to walk forward in just 6 seconds, which is really hard to do if you try to use something like reinforcement learning, because reinforcement learning is very, very noisy, unfortunately, and sample inefficient. So this will converge faster than using reinforcement learning, and it will also be able to solve some problems that it can't. Caveat, it will also be unable to solve some problems that reinforcement learning can. And that's because a gradient-based approach just like this is really intuitively a greedy approach. So if it needs some sort of exploration as well, then you're going to want to go to something that's a reinforcement learning type approach. Okay. There are a whole bunch of different auto differentiation types, and whether or not you have a large output of your system or a small output of your system or a large input of your system or a small input of your system, you're going to want to choose different types of differentiation choices to get your gradients. And I also want to note, though, that if you're going to do backpropagation, that's going to be very, very memory intensive for large systems, because you need to save the information. You have to checkpoint it at every single layer of the system for when you do your backpropagation pass to compute your gradient. So if you have a very long system, if it's a very high dimensional system, which can happen in soft robotics, then this is going to be something that's going to use a ton of memory, and you're going to run into some serious problems. So one way to ameliorate this problem is to change the integration time. So the integration time is a function of the stiffness of the system. And unfortunately, you have to pick a time step of using an explicit integrator so that the system doesn't numerically explode. And that time step for a soft robot looks something like 7 microseconds, which is extremely slow. You're doing 1 million simulation steps in order to do 1 second in real time. You're going to run out of memory with 1 million steps, each holding maybe 1 million data points, like really fast. So you can use implicit integration, which will allow your system to be a little bit less accurate, but it'll be much more stable. And you can take larger time steps and you won't run out of memory. So that's 2 benefits for the price of 1. And the drawback is that your simulator is going to be a little less accurate. Usually, I would argue that a less accurate simulator doesn't really matter too much, unless the accuracy that you're decreasing it by is very, very large. So small hits to accuracy are usually not a big deal, because your simulator was wrong to begin with. Like, the model is wrong, and when you actually bring it to the real world, there's going to be a whole bunch of changes in the way that you actually fabricate it based on the virtual design. So this should only be used as some sort of, at least at this stage where we don't have robust sim-to-real pipelines for design. Right now, you should think of this as you want the simulation to guide you, but not to be something you take as as faith. There's been a lot of other work that's been doing this type of thing with implicit integration more, especially in the clothing regime. So you can check out a paper called Diff Cloth as well. And the area of differentiable simulation now has grown to where you have rigid body simulations that are differentiable, soft body simulations, fluid dynamics. You can even find molecular dynamics differentiable simulation. And if you want to play with this at home, I really recommend checking out two domain-specific languages. There's Tai Chi, and there's also NVIDIA Warp. These are relatively easy to get started with, and they give you a bunch of starter codes so you can build some cool demos pretty quickly. We also wrote a review article, if you want to check it out, that sort of brings together and marries the ideas in one differentiable pipeline from differentiable geometry, physics simulation, and rendering and vision. So that might be especially relevant to people who are interested in the connections between physics and optics. If you want to check out some demos and play around with this yourself, I whipped up two demos. We don't have time to really do a hands-on demo here, but these were originally for a previous tutorial, but I think they're still just as relevant here. And you can learn about how to use differentiable simulation and also use it for co-optimization. And additional resources, these are some very popular physics simulators and control toolboxes that you can use. Highly recommend checking them out. Majoko, I used to not like so much, but it got really good recently. So it's now in JAX. So it's very fun. Okay. I'm going to quickly talk about just a few other ideas in control because they'll be relevant as I go more into the co-design aspect of this talk. So three types of controllers. You have open loop controllers where you prescribe what the motion is going to be. You have closed loop controllers, which repeatedly online will recompute. Obviously, these are more expensive, but they will recompute based on the state and sensing, what type of actions you should take. And then there's some methods that can be thought of as an online method or an offline method, things like model predictive control or reinforcement learning. These do some planning offline or online, and then they do some execution offline or online that's similar. So one very common way to do motion planning and is relevant to some things we're going to talk about later is something called trajectory optimization. I'll go over this pretty quickly, but the idea here is that from some sort of starting configuration and some sort of goal configuration, what are the motions that you need to get to take you from the start to the goal? So this becomes an optimization over what are the actuation values. And also, in order to make this a little more tractable, we add additional auxiliary variables, which say that what we also want to solve for what are going to be all the intermediate states. So the real thing that this becomes is a constrained optimization problem, which says that all these intermediate states that we're going to solve for, we also need to make sure that they are physically coherent, that if you have also the control input, that they time integrate to get you to the goal. And this can be very, very powerful. So come on, play the thing. Oh yeah, is this gonna happen? This is all right. Check out this paper, has a video. If we can't get it to work, if any other videos have any problems, sometimes that's the case. I'll try to show them offline or I'll restart PowerPoint. All right. Let's see if this one works. This one's working. Okay. So I'll try to find the other video for you later, but there's also model predictive control is another approach to, and this is a really great control algorithm if you just want to get something that works immediately, maybe not optimal, but is going to be pretty robust and reliable. This looks a little bit into the future at any time during its simulation. It forecasts a whole bunch of different outcomes if you were to take different actuation strategies, and then it picks the best one or it blends them together, and then it recomputes a new horizon. So it's constantly recomputing horizons. It's very, very expensive, but the benefit there is that it's sort of doing a Monte Carlo search of all sorts of different possible ways in order to move throughout a space. And so you can use this in order to have some exploration built in. And lastly, the most popular way today of doing control is these neural networks I've been talking about. I'm sure most people in the room are familiar with this, but reinforcement learning is able to really efficiently-ish design controllers for robots. The harder the task, of course, the harder the more it becomes not efficient. But for a lot of things these days, like walking or manipulation even, some of these things you can solve on commercial hardware, like a laptop in an hour or less. So in simulation. And increasingly, these things are translating to the real world. So I want to bring a couple of resources if you want to read more about this type of material, especially trajectory optimization or reinforcement learning. You can check out some dedicated tutorials to that. And Underactuated Robotics at MIT is a really great online textbook that gives sort of an overview of all these different methods. It's a little dense, but it's pretty good. Okay. Last thing for the first half today, I'm running a little bit behind, I guess, because we're at the 30-minute point. I want to talk a little bit about some traditional methods in co-optimization, which is a weird thing to say because this field is really only like 30 years old at best, probably, for robotics at least. But I mentioned that the goal here was that we want to design over the body of the system and the brain of the system and all the different components simultaneously to get something that's going to be really highly performant. And I would say that broadly speaking, there's three approaches to doing this. One is these large types of heuristic searches, evolutionary searches, things like the Carl Sims work that I'll show in just a second. And then there's going to be gradient-based approaches that are going to use these differentiable simulations in order to efficiently search for optimal configurations. And then to provide a little more exploration, similar to reinforcement learning, they're going to have some generative-based approaches that are going to use learned models to propose ideas and then grade them and then recompute. So maybe I don't have to show this exactly again. This was, I'm going to skip over this. I'm worried that the videos aren't playing. Okay, we'll figure it out. This was just going to be the Carl Sims video, which Amir showed earlier today. Oh, now it plays. I don't understand technology. Okay. The way that this algorithm works, though, where in order to do an evolutionary algorithm is assume you have a population of different robots. You evaluate how well those agents are going to perform. And part of that, of course, is going to be to have to generate some sort of controller. So you generate a controller for your morphologies, and you see how well they perform according to some metric that you care about and some environment that you care about. Then you have to then decide, how do I look at that population, and based on that feedback, modify the population and decide what I'm going to sample next, what I'm going to try next. So here you have some way to do modification, and then you resample based on what are the best performing robots. You do these two things sort of simultaneously. And that gives you a new population of robots. And so it's this procedure where you're constantly filtering on the best robots and maybe tweaking them a little bit so you get some exploration built in. So these are sometimes thought of as chromosomes, some sort of binary string or some sort of floating point string. This is your design space, will be translated into some sort of robots. You need this, some sort of generation function. I would say this approach is really also not that dissimilar from particle filtering, which sort of does an intelligent resampling of the particles to track objects. So if you're familiar with this method, classical vision approach, then this should also make sense. Most design algorithms will look like a bi-level optimization procedure where you are, as I just showed, you choose some sort of morphology of your system, you do some sort of control optimization, and that also has an inner loop, that simulation itself. So that can get very, very expensive. Here's some work if you want to get started with playing around with something that I just showed on the previous slide. There's a paper called EvoGym, and you can basically try these types of algorithms in real time, and it's actually pretty efficient. Some problems it solves, some are, I think, unsolved. Now people are using this as a toolbox to try to prototype different types of evolutionary algorithms. It's a little bit limited in resolution, of course, but it's also a pretty fun sandbox and yeah. So evolutionary algorithms can be pretty slow, but they are also pretty quick to get started with. So ultimately, you see all these cool emergent behaviors come out of this. And you really just want what I just showed you on the previous slides to be done faster, and you'd probably be pretty happy, right? If you got the Carl Sims stuff pretty quickly. So of course, using gradients is one way that we're going to use to speed this up. And this is the last thing I'll talk about, I think, in the first half of today. So in Chain Queen, I showed you this slide earlier, but now what if we also wanted to optimize over the material properties of the system? So the material properties may be spatially varying of each particle. So sort of think about how I'm going to design the skeleton of the system by programming the stiffness or the compressibility or the density of every particle in the system. And this is going to add way more variables than you just saw before. But I want to highlight that this can be done really, really efficiently with gradients. Even though this is maybe a 100,000 design variable problem, you can see that over time, the system is going to be able to find more and more highly performant design. So these are distributions of different materials. And they also look a little bit biomimetic. So over time, you'll see, like for this quadruped example, it wants to run forward, and you'll sort of see areas that are redder, that these are more incompressible areas, and also feet patterns that sort of look like they're stiffer at the push-off point and softer where it's going to land. So it all also makes intuitive sense. And I want to drive home that for every single design variable that you add into the system, performance tends to improve. So it can cut through these really, really high dimensional problems. If you're adding stiffness as a design variable, the performance will improve. If you're adding Poisson ratio as a design variable, performance will improve. If you're adding density as a design variable, performance will improve. And when you search over control and design simultaneously, co-optimization always wins out. So the blue curves here you see, that's pure control optimization. And the gray curves at the top, those are when everything is considered at once. So even though this is high dimensional, this is not a problem for the curse of dimensionality. Lastly, showing you how you can use trajectory optimization to also optimize over rigid body parameters. So I showed you earlier, you have these problems where you want to start from some sort of starting location and you want to get to some sort of goal location, and you need to search for what are going to be the controllers and the states that are going to, the path that's going to get you there. So what are the control inputs that you need in order to solve this? I'm just going to go a little bit quickly here. There's, of course, these complicated constraints that I say have to be filled out and satisfied, but you can actually reason about these really quickly with today's second order optimizers, specifically sequential quadratic programming optimizers. So that's fine. And then the question becomes, what if you also want to not only optimize over control, but also over design variables? And again, one of the most beautiful things here that I can say is that it kind of just works. So if you build a differentiable system that can differentiate over your gradients of your design variables, and also you can compute the gradients of your control variables, and as long as you make sure that you have contact constraints so that as you extend your system, it doesn't penetrate the ground or do something that's crazy with its environment, right? If the legs get longer, they should not go underground. The body should move upward. Then you can get co-optimization of these systems. So give an example of this. If you have this parameterized geometric system, and your goal is you want it to move forward and you want the middle of its body to hit that red point, it's too short, first of all, to do that. So the parameters are going to have to change. And you give it just some sort of initial guess as to what that trajectory is going to look like. And this really matters very little, honestly. Then the system can automatically co-optimize over what are going to be the optimal physical parameters of the system, as well as what is going to be the controller of the system. As well as if you're really intelligent and you choose, I want to make my objective function minimize the maximal torque, you can sort of use that to choose what type of actuators you want. So you can use your objective function that you care about to choose, minimize the amount of energy that you actually need to solve this. So I'll just show one more quick little video of this. I think I showed this one already, actually, so maybe this isn't as exciting. You can bring this to the real world. Of course, there's a gap, some trivial gap, of course, mostly on friction parameters, which is always the sticking point, no pun intended. If you want to build AT-ATs that have ridiculous gates, you can also do that. So it can also solve if you need it to go uphill, front legs shorter, back legs longer, so I can stand. And there's been some work by colleagues on how do you co-optimize these systems over, or actually do interactive search after you've actually optimized these systems, where as you change the parameters interactively, it will also, the physical design parameters interactively, it'll also search for what are going to be how do you change the control parameters in order to compensate. So I'm running a little bit behind. I think I'm running about 10 minutes behind. I'm going to let this video play. I know this is a whirlwind introduction, and I want to stop and see if there are any questions. No. Yes. the goal is an image like I want to reach this image in the world. In that case, you would have to essentially have some sort of function that when it sees that image, it provides some sort of signal mathematically that it has achieved its goal. So if it sees the image at the end of like a maze or something like that, if it's doing a navigation task, then if you want to do like a reinforcement learning type approach, you can give it a really large reward. Or if you're doing some other approach, if you're doing more a penalty function type of way, you can not penalize it for actually reaching the goal. But in general, you have to give it some sort of signal, some sort of score about how good it's seeing that image. And then through optimization, it will promote strategies that will see that image more often, because that leads to a higher score. And that's where the gradients come in. Whether you're doing a reinforcement learning based approach, or if you're doing a model based approach, you'll use gradients either from data or from the model in order to push the parameters of the system based on feedback of the simulation to see that image more often. This is the high level. Since I'm trying to give like a general overview today, I'm going obviously through this a little fast, but for the actual methods, I can send you more information in terms of those tutorials, for instance. Yeah. Other questions? Part 2. Okay. So this is where the new age stuff sort of comes in. And so I might need to go a little fast or skip a section at the end. We'll see how we're doing on time. But I want to at least bring to you guys the generative design side of things, which is now growing in popularity, and also talk a little bit at least about fabrication and the sim to real gap here. So, of course, if you want to use generative AI in order to design something, then the obvious question is, just ask ChatGPT to do it for you, as long as it's not having an outage. I heard there was an outage yesterday. Okay. And so I did this, of course. I had to try this because what if I've been spending the last 10 years coming up with algorithms when ChatGPT can just solve it for me? So I asked it to generate for me a strawberry picking robot, something that can a soft robot that can grasp strawberries. And it tried, of course. So it generated me this thing that looks like an arm, but actually is a completely locked linkage, so not very good. And then it also tried, of course, arms that just float in the air with 2 hands. I guess this is not a good idea either. And these are the most sane examples, because after here it's just some nightmare fuel. This is not a strawberry picking robot. This is just a spider strawberry, and that's nightmare fuel as well. Okay, so that's a ton. Okay, anyway, so these are bad solutions. Why does ChatGPT come up with bad solutions to this? This is not a hypothetical problem. We did a big study where we tried to do this more with furniture and robots. We asked ChatGPT to generate different designs. That's a car. Don't get in that car. The wheels are sideways. Please don't get in that car. You put enough elbow grease, you work with these LLMs. Yes, you can get them to make cool things. But in that process, you also get a lot of generation that look like floating tabletops, which are just really frustrating. The problem here is that there's no visual intelligence and there's no physical intelligence. So there's no certificate of performance. It doesn't know whether or not this is a good tabletop or not, because it can't simulate it and it doesn't know its function. So simulation is so important throughout this whole story, whether it's for computing gradients or whether it's for just checking something's going to work in the real world. If you're going to propose a lot of things, you want to be able to check if they're going to work. So this is a recent project that we worked on in the soft robotics space called DiffuseBot. We go from specification of here's an objective function, or you can do it from language, generate it, use this to generate some diffuse 3D geometry and actuators, and then simulate this, and then use that as feedback in order to optimize the system. And eventually we brought some of these to the real world. Okay, so this is an example of something has pretty fast simulation. It's optimizing, and now with the ability to do some generative sampling, now you can start to explore, and this is really nice. So I'm sure a lot of people in the room now are familiar with diffusion processes, but the idea is you have some sort of data set, you add a bunch of noise to it, and then you get some sort of noisy version of your data set. And you want to come up with, learn some sort of inverting function. What, if I want a cat, how do I generate a cat from this noise? What is this denoising process? That's a machine learning problem. And it's also one that requires conditioning. It's one that requires conditioning on saying, I want a cat, because from that noise, you could really denoise it into anything. Get a dog or a baseball bat or anything, right? So in this project, we use an off-the-shelf diffusion process called Point E. This is something that was released by OpenAI about 1.5 years ago, I think, for creating point clouds. I think it was one of the first 3D geometry diffusion methods, and now there's a ton of them. And we just use clustering based on the geometry in order to choose where to put the actuators. There's your actuators. Okay. And then for control in this example, to keep it a little simple, we're going to use open loop control. So just your time varying signals. Normally in Point E, the way that this works is you have some sort of text input, and then that's going to be diffused over time, and that's going to involve some sort of transformer in the loop. Ultimately, this diffusion process has a lot of computations that go translate language to some sort of embedding. We can work directly with that embedding. We don't need to worry about the text here because we mostly want to see how well something that we search over is going to perform in simulation. So this algorithm that I'm going to show you has really two main steps to it. First, you propose a robot and you evaluate how well it performs, and you put that into a data set, and you're going to try to move your data, your embeddings that you're using in your diffusion process in order to come up with a high-performant robot. And second, as you're doing this diffusion process, you need some sort of feedback because you can't use language to say whether or not something is going to perform well. You need simulation to say whether or not something is going to perform well and some sort of objective function. So we'll use some simulation in the loop here in order to steer this to highly performant robots. There's some dirty work you have to do up front here, which is to say that these representations in the middle, if you want to simulate them, not so good. So we need to make them a little bit denser. So we have a process called robotization, which can be made differentiable, which is just the main thing I want to note here, because differentiability is going to be very key to this. And so we can convert the sparse point cloud into a denser one. And I said for actuators, we're going to use k-means clustering. That's a discrete process, but it turns out you can approximate the gradients very, very accurately by assuming that the importance of the actual simulation gradients with respect to the actuator labels is basically 0. The geometry matters most of all, and that also affects the clusters themselves. So, okay, so those two main steps that I talked about, from some sort of embedding that we want to search over, this is our search design space, they're just floating point numbers. We want them to be diffused into a highly performant robot. And also on the side, we're going to have control inputs that I don't draw here, but those are also going to have to be optimized. So the way that this works is we are going to propose some robots, and we're going to basically do something that's similar to reinforcement learning, where we're going to generate some candidates. We're going to see how well they're going to perform based on simulation. And then we're going to throw them into a data set. And we're going to keep the best ones, and we're going to throw away the old ones. So this should also sound a little similar to evolutionary algorithms. And then in a learning phase, we're going to every once in a while, take this data set, and then we're going to do some sort of stochastic gradient descent, simple supervised learning problem to just, for an objective function to move the embedding towards something that's going to perform well. As we do the diffusion process itself, like I said, we need to condition it on something. Usually with images, you use clip. Here, we're going to not be able to use that. We're going to use physics instead. And so our biasing method, our conditioning method here, is actually going to be exactly the gradients from simulation with respect to control and with respect to design variables. And so this is a nice way to link what I just talked about earlier about differentiable simulation, optimization, and generative processes all together, and shows you how you can use this to really efficiently design robots and soft robots in simulation. That's the whole algorithm, and it can just by changing the objective function and a little bit about the environment, you can get a whole bunch of different cool, different types of diverse outputs. So here's sort of the zoo. If you care about, I have an objective function which says, please balance on the top of this pole or land on that pylon. So it just looks at, I want the distance at the endpoint to be basically on top of that or at the bottom there. It'll generate things that can land the robot in those locations. If you say, I want the robot to move as far to the left as possible in a certain amount of time, you'll get different types of locomoting robots with different types of behaviors depending on how you set up your environment. And if you care about, if you set your objective to be something about the environment, like certain objects and where they end up at the end of the simulation, then you can get some sorts of different types of manipulators. And this diffusion-based process, which includes some exploration here, will also beat out a lot of the baseline methods. Almost all of these examples were the diffuse bot method was better, and also intuitively it makes a lot more sense. So you'll see, on the right column here, these things look like things that can solve the problems that you care about. That thing on the bottom left there, that's a gripper that doesn't look like it's going to be very good at gripping. That block of cheese is not going to land very well on the pylon, and so on. So this makes a lot of sense. And if you want to condition this with aesthetics, that is also possible because you can add back in your clip objectives as well. So if you want it to look more like a ball, then you can ask it that, and you can trade off how much you care about the aesthetics of what something looks like versus how well it performs. Or you can say, I want it to be wider or thicker. And of course, I showed you this earlier, but for at least simple dynamics, you can bring this to the real world. For more complicated dynamical systems, there's a big simulator mismatch. Okay, I want to get through one more example of ways you can use generative AI to do design, because this is really important for the perceptual side of things. So this is the one thing I didn't show you here is what if you want to design your sensors of your system. I showed you open loop control, but for doing closed loop control, you also need some way in order to have sensors placed down on the system and used as feedback. So this is especially important in the real world, right? Because you want proprioception. You want something to understand where it is, how its body is configured. And you also ideally want to be able to do navigation as well, right? And you can't motion capture the whole world. You can't, set up Vicon systems in the world or external third-person camera viewpoints. So we need things that can sense within a robot how it's going to move, what its joint angles are going to be. For rigid robots, that's often encoders. For soft robots, for squishier things, that's requires a little bit more type of strain type sensors. So where do we put these strain sensors? One of the things that we found out here is that humans are really bad at this, and computers are very good at this, and I'll get into that a little bit later. So given some sort of task that you care about, such as I have a gripper and I want to identify this shape, and also you have the opportunity to put down sensors, how do you simultaneously solve this classification task and the sensor placement task at the same time? So this is another different type of co-design problem than I showed you before with all these locomotion examples. This is more of a reasoning one. And this ultimately is going to come down to a clever representation that is going to generalize over lots of different morphologies. And the way we do this is that we have an architecture where we basically have a neural network architecture that works on point clouds. It's not super fancy, but for the input layer of the system, we allow it to change whether or not it's going to have a strain sensor at any given location or not. So each input to the system represents a single particle's strain in its vertical direction and its horizontal direction. So how much it's stretching. And then what we're going to compute here is, we're going to solve for here is weights in the network that say how well that basically do the classification task, and input weights that are going to be forced, most of them sparsely, to 0. And by forcing those weights to 0, that means that we're going to ignore a lot of the inputs to the system. And by choosing which inputs we ignore of the system, that tells you where you should place your sensors in your system. So this is one clever model architecture that you can now train with a supervised learning setting, and it's going to automatically for you simultaneously optimize and solve for where you should put your sensors at the same time that it learns how to solve the task. This is based on something that is going to have a penalty function and a representation in the neurons that is going to ultimately force the sensor distribution to either exist or not exist. And this process is going to be done throughout the learning process. You're going to stochastically, generatively sample a whole bunch of different sensor arrangements. So at the end of the day, if you want to learn something that is also going to be generative and propose different types of sensor placements, you can also soften the necessity that it goes to 1 or 0. And sometimes we found some solutions where some of the sensors are 50-50. So either solution would probably work pretty well. So we have this one penalty function that you have to add onto your typical learning process to force most of these to 0. And this, our training algorithm is just build the data set, compute the loss that I just showed you, and then optimize using backpropagation through the model. Okay. So just to show you guys a few different tasks, I showed you this if you want to determine, what shape are we grasping? Is it a circle? Is it a triangle? Is it a diamond? Or is it nothing? Then you can get really good performance with just 5 sensors. So this is sort of similar to the few oh my gosh, I'm losing the name of this, the photoreceptor case. Here, this is sort of the equivalent with just a few tactile sensors. You can get really good classification as well. But you have to do this co-learning process. You need to, the positioning really matters of these sensors. If you try to do it at random, you'll find that a lot of times that the random configurations actually lead to very bad performance. The converged sensors placements really make sense. They go where the system moves most dynamically and where it's going to interact most with the environment. And this is what humans get wrong, because they tend to, in our experiments, choose just places that are interesting geometrically, even if those places don't actually move very much. So we've done a lot of reconstruction of these systems, and you can see, oops, sorry, for these different types of trajectories, then, oops, not cooperating. See if I can do this. Yeah. So these are the different types of reconstructions: ground truth at the top and the reconstruction at the bottom. And the big circles you see, that's where the sensor placement is. The color maps represent the velocities as well. So we are able to reconstruct not only the positions of these systems pretty well, but also the velocities pretty well. And we can also do this in 3 dimensions. So sort of you getting the orthographic views of this thing. And the left and the right represent, what matches and what doesn't. We can outperform human baselines, of course. I mentioned this earlier, quite significantly across the board. And yeah, I guess I'll skip over this for now. One other method, which I don't have time to talk about today, we have one for rigid robotics as well. This is more your jam. And this is it's very similar to DiffuseBot, but you're going to be sampling from a grammar, building up these rigid robots, evaluating their performance, and then training a model based on that. So if you're interested in playing around with this as well, we also set up a collab for this as well. So feel free to try playing around with it at home. It's a little slow on Colab. This is CPU core heavy, and Colab doesn't give you a lot of CPU cores. So the code is also open source, and you can try this out yourself. It takes about 1,000 simulations, but each one of or generations, I should say, each one of those generations only has one robot that it simulates, but the simulation itself is expensive because it's doing model predictive control. So that's the tie-in also to model predictive control. All right, I only have about 2 minutes left. And so to wrap this up, I'm going to go really quickly, I think, through the fabrication and the considerations on the material side of things. I'm going to skip some of the method slides. If people want, I think we'll disseminate these later, or you can reach out to me, and I'm happy to send over some slides. But I really want to talk at least about what the considerations are as you want to try to bring these things to the physical world. So I'll focus on those slides here. One of the challenges that you have is that when you actually want to physically fabricate these systems, you have this problem of, well, this might require crazy material gradients. Every single droplet has a different material. How am I going to fabricate something that's made out of thousands of different materials? Right? That's really, really difficult to do. And so what you need is some other translation method where you can, in order to realize your body, you have some sort of method that maybe abstracts this away. It simplifies it, comes up with some sort of representation that is actually fabricable. Fabricable is the key word there, because one way we've been exploring this has been in machine knitting and making textile-based robots. So just to show this really quickly, by having different swatches in these different areas, you can actually program what is going to be the stiffness with different microstructures. So even though you can only have a single, maybe discrete materials that you're working with, in this case, different stitches have different stiffnesses. Then when you combine them into together, you can make microstructures that have different types of emergent behaviors. So it doesn't allow you to necessarily program it at the very, very small level what every single material is, but at the larger level, you're able to realize a large swath of materials themselves. And these are examples of what the different swatches we played around with look like. Some are made with elastic materials, some are not, and some are made with conductive materials. So we could also realize the types of sensing, strain sensing that I talked about before. And I'll show, for the sake of demonstration, at least cannot play media, fantastic. Never fails. Show this video. Nope. All right. First of the live demo. I'll show this first video, which was going to play anyway. So this is I'm going to skip to the end here for the sake of time. A fabricated robot. It's done with inflatables, but you'll see here that there's different types of stitching here and there. And based on what type of material you put down, this allows it to actually bend in a certain direction when it's inflated. Okay, I think videos are going to be a little bit tricky. All hell. Yeah, cannot play media. I don't know. When you get through 30 videos, it just stops playing media for some reason in PowerPoint. Go figure. Okay. The other problem that you have is not only a problem of physically realizing these robots, but also when you build them, are they actually going to match the real behavior? There's a whole bunch of different ways, just to give a quick overview of how to try to make your systems more accurate so they more faithfully model the world. Aside from just better modeling, which is always a trade-off, as I mentioned earlier, you can do things like system identification to come up with better parameters of your system that are more accurate when brought to the real world based on real-world video data that you have. This will get you only so far. So there are other approaches that people have also come up with more recently, things like domain randomization, make sure that you're robust to problems in the real world. Adapt your system, at least the control side you can adapt. It's harder to adapt the physical designs, but you can adapt them after you've built them. You can modify the controls with some online reinforcement learning. And you can also add learning to your physics itself. So you can use real world data to learn new physics engines that are able to, or hybrid simulations, which are able to have the best of both worlds of having an analytical simulator and also some learned fine tuning. And again, this is an inverse problem. So I'm going to skip to the end here now. And I really just want to end with a few notes here about what are the important problems that are left here open and what we should be focusing on as a community going forward. You know, we want to build these ecosystems where you design something, you're able to fabricate it, you know that it's going to work when you bring it to the real world. And the question now is going to be, how are we going to use the data from the real world in order to really inform the design process itself? I think this is extremely important. And that's going to require fabrication cycles where you can propose a design through some sort of optimization, fabricate it really quickly, and then test it and use that as feedback in the simulator itself to improve the models. I'll skip over some other things, but I really want to say that the opportunity that we have here is that this will lead to faster design processes, ability to do more exploration if we get this right, and come up with new ideas that we haven't considered before. We'll save resources by reducing the number of failed prototypes that we have. It will democratize creation because people without an experience in mechanical engineering will have some ability to do some work there, and mechanical engineers should be able to go faster with more computational tools. And finally, I'm really hopeful that this will also allow computers to run their generative processes and sort of learn from their own experiences and maybe be able to design on their own. Open hard problems, of course. How do you do sim to real, not just for control, but also something where designs are going to transfer for any robot that you consider? How do you make sure that when you transfer something to the real world, that if your problem specifications change, that it's actually going to also, be able to adapt to the real world? And how are we going to reason about all these different systems simultaneously? I showed you examples that maybe had 3 of these, like actuation, planning, topology, materials, sensing, but not all of these at once. And so with that algorithm that can reason about all these different aspects of a physical system, much like biology, that still sort of eludes us right now. And maybe foundational models will be the way to do that. I don't know, but I would not be surprised if by combining all these different types of generative technologies together, that will build systems that are able to reason about the vision, the physics, the text, and everything, and be able to think about how things are going to work when they're built. All right, I'm going to skip over this, and I think that should bring me to the end of today. So sorry that was a little bit extended. I think 1 or 2 minutes over, but happy to take questions, maybe 1 or 2 quick ones, and also happy to talk more offline. I think we have only 1 more session left today, and then people can feel free to mingle. So thank you.
So in the meantime, that set for the neural concept talk, if there are any questions,